Okay, everybody. Well, let's start up our yearly meeting. It's been about a year and a half or so since our last team meeting, September 2024. Also because of all the insanity happening with this agency and our former presence in 2880 Broadway. So thank you all for making it. So we will move on. I just have a few slides. I'm going to give some updates on stuff that I've been up to and stuff that I think all of you are aware of. Just first, I mentioned that I started at NASA 25 and a half years ago, right after I took a trip to Ladakh and the rest of India for 6 weeks between jobs. I never thought I would stay at this agency for 25 years because I could never imagine myself being any place for 25 years. And that tells you just how non-radical I became. They crush your soul in these places, make you think you should stay there for life. But I haven't. Anyway. Anyway, I highly recommend Ladakh. It's a great place to go. It's completely unlike everywhere else in India. And this is where I'm going to start working February 1st or February 2nd, as you please. You're all welcome there. This is Ångström Laboratoriet. I think you've all heard of Ångström, and you can imagine he's a very proud member of the scientific community. It's they named giant buildings after him, including this one, which is a monstrosity. All of engineering, physics, chemistry are in this building. Okay, these are our current team members. It's amazing to me how many people are in this team. 21, apparently. I'm always telling people it's more like 12, but I'm always wrong. I think you all know everybody. I just will mention a few things. As you all know, Andy Ackerman retired, our clouds expert, but he's still helping out. I would just say anybody who needs clouds help from Andy, I would suggest doing that in the next couple of months because Andy, as maybe you all know, is an avid sailor. And in the spring, Andy's leaving with his lovely wife to go sailing in his new French sailboat in Europe. So I suspect he will be very hard to get a hold of at that point. Igor's here. Rory Barnes, as you all know, is our dynamics expert at UW. He is in the middle of an XRT proposal, so he may not make it. Mark Chandler, of course, is one of our paleo people. Andrea, unfortunately, fell ill this morning, so I don't know if she's going to make it. Clune, you all know, handles the calendaring system. He's working with Andrea to get that implemented in E3 and Planet 3. Chris is here in the room with us. He's going to give us a talk. Cultural, our new MPP, who we've been working with for a couple of years already with John Marshall at MIT, will be with us for the next 2 years at least. Donnie Glazer is going to be most likely at UW, University of Washington. Scott Guzewich, I don't know if Scott, so Don made it. I don't know. Scott said he might not make it in the beginning, but anyway, you all know who Scott is. He's going to take over as admin PI since I retired. Sonny Harman is not going to make it today. Nancy is online. She's going to give us a nice talk about land surface and biosignatures. Kevin Knuth fell down with the flu apparently yesterday. So his postdoc Vasuda will be giving, or his graduate student. I always think she's older than that, but Vasuda's going to give his talk and her talk today. Tony's in the room here with us doing our ocean modeling and sea ice. Rakesh is online with us, who I've been working with for a few years on this Pioneer Venus mass spectrometer in situ data. Jan is doing our Mars dust work, and he's going to give us a talk about that. And Robert Pincus, we're very honored to have join us from Lamont Doherty today to talk about some work that he's interested in doing with us. Linda just popped into the room, our other paleo climate expert, and she's head of the cuisines team. Kostas could not make it today for various reasons, and I have a recorded talk for him, which I'll talk about. I remain a slave, as I say here, and Eric Wolf is our ready to transfer person. Let's just put an alphabetical say. So not too many changes. Everybody's stuck around. The budget, as you all know, is very precarious, mostly because most of the team is paid at least half or more out of the earth science budget. And as you know, the earth science budget is under great strain, and we don't know what the long-term prospects for that are. And I'm very concerned, like the rest of you, about that. I could have taken the DRP, by the way, which is the deferred resignation program, and that would have meant I could have left in August and given the agency the big finger and gone about my way, but I didn't do that. I stuck around to try to protect as many of my people as I could. I'm not saying I was completely successful, but I did the best I could. I want you all to know that because I care about this team and the success of this project. Okay. These are things that are under development. Not much has changed since the last talk, I would say. So I'm not going to really go through all these per se. I would just mention a few things that I thought were important. The KPP chemistry stuff has got some new initiatives from the Earth side of the house, and Kostas remains optimistic, which is remarkable given how many years we've worked on this and made very little progress. The Planet 2.0 paper was released and published. I'm very happy about that. That was a long push. That paper began when Tony was still here. Tony and I, Kostas, really, and with help from Igor and many other people, got this paper through. I'm hoping that we may get Planet 3.0 released one of these days. A lot of it depends upon Andrea working with Andy and Max on some aspects, and Igor's also pitching in for some of that, and of course Tom helping get the calendar aspects merged in. And of course, as we all know, we got the ocean biogeochemistry stuff working with help from Paul and Natasha, and they've written a nice paper on that last year. Okay, so we didn't run a tutorial last year, again, because it was insane. But last week, I ran a tutorial at University of Arizona because I was asked to. And I thought that was very nice. I encourage you all to do that. If you go somewhere and you're giving a talk or something, offer to run a tutorial. It's not hard. We have all the slides. Everything's online. It's more just to get people introduced to the model and get them to use it. And the more users we have, the better chance we have of getting someone to help us do development of the model, I hope.
Was it mostly students or researchers?
It was mostly students. Yeah. Ty Robinson was my host, and he actually showed up. I think he's the one who actually took this picture. So it was good. It was a good time. I think the last one I had done before this was a few years ago in Japan, of all places. So I highly recommend that. And probably this year, maybe later this year, we can try to run it again because we really haven't updated the slides for Planet 2.0 that much. Not that much has changed, of course. Okay, so my own community service beyond that, I had a master's thesis student in Uppsala meteorology. You can see her thesis paper there on the left. I had six students on a bachelor's thesis project in environmental engineering of all things. And then two of those students did another project course with me afterward, which were quite successful. I was really happy with that. They used Kopp and Geiger, and they generated Spectra from PSG. They did all the things that we want people to do and use with our model, which worked pretty well. And these were all, they used simulations that I had developed over the previous years. As you can see here, TRAPPIST-1E for the most part. And some Permian and postmodern things. I'm not going to go through all of my stuff I did, but I've got a few papers out in 2025. I've got a few that are in press or just waiting for the final referee report, and then a whole bunch of stuff that I'm working on, some of which Rakesh is going to talk about a bit later, and then some other papers which I'm expecting to submit this year, although at least one of them I suspected I was going to submit it last year, but it turned out to be much harder to finish that paper than I expected, to be honest. Probably more just because of my own paranoia about doing things in a good way. Yes, so what about our future? I talked about this a little bit. The budget from the ICAR, which is our main source of funding, has been dribbling out as CRs are passed and the budget is passed and all that sort of stuff. The program manager has been pretty good about sending the money along as she gets it. But now that I believe we have a budget, hopefully we'll get the rest of that on board. I was afraid we wouldn't get so much money because there were several colleagues at Goddard were saying that they were raiding people's budgets to pay civil servant salaries. To be honest, that was attempted, but I foisted them off at the end of last fiscal year somehow. But anyway, we only have one SEEK project at the moment. As you all know, the SEEK funding is a really good opportunity for us to get funding, and I highly recommend to do it. Why? Because it's only 2 pages instead of 14 pages and endless budgets and crossing T's and dotting I's. So that will come out in the next month or two. So please think of a good project and apply for it, because we have one now. Andrea's leading doing some ancient Mars simulations, but that money runs out this year. There are, I think, some possibilities. I thought even more so beforehand for ESMD funding, that's Exploration Science Mission Directed, Moon to Mars stuff, to do modern Mars modeling. So we'll see if anything comes of that. But I think the work that Jan and Kostas and Igor have been working on for the past few years could have direct application there. So I hope that we see some calls for funding that in the near term. And
Mike, I have SEEK funding for this year also.
Oh, you do? Okay, I'm sorry, Nancy. Thank you for pointing that out. I didn't realize that. Got it. And I always say this every year: we need to write more proposals. I already said it about the SEEK, and we need to write more papers. Now, I don't know if you all realize this, but you know the SSW Solar System Working Program, which Rakesh and I have our grant on right now, doing the Venus stuff, has been merged with Habitable Worlds, and now they call it SSS or S cubed, and they've changed completely the way you write proposals now. Now it's a 5-page proposal, no budget. You just say if you fit in the low, medium, or high category. They tell you what those are. I highly recommend you apply to that just because it's only 5 pages. I'm not saying your chances are great, but it's much better to spend your energy writing a 5-page proposal that has little chance of getting funded than a 14-page proposal, plus dotting all the crossing T's, I's, blah, blah, blah. So I highly recommend that for the next fiscal year when S-Cube comes out.
What does the acronym stand for, S-Cube?
Solar System something.
Science.
Solar System Science, yes, sorry.
Science. The biology got rolled into that as well.
Yes, exobiology also. Yeah, I was thinking there was another program that was rolled in. I forgot.
So is that and SEEK both through NASA, or what's?
SEEK is an ISFM direct funded through Goddard Space Flight Center. So they run their own call basically every year.
During the GEES meeting yesterday, Gavin was saying that he was at a HQ last week and that ROCKE-3D actually came quite a bit. What's your degree of confidence that we could get some of the money going from Modeli to go to ROCKE-3D as well?
I say very little at the moment because I have not. All I've seen is a lot of talk. And when the big managers came here and they talked to us, they didn't say anything about. I mean, they knew about us, but they didn't say anything about the funding. Gavin doesn't have funding himself, so I mean, until he gets funding, I don't see how. I don't know. Sorry, I tend to be pessimistic about this.
Yeah, this virtual institute people who came, they basically, first of all, as I said, that they don't want community model. So I guess
we're a community model.
Huh?
And we're a community model.
Yeah, so I guess they are not that much interested. If virtual institute thing goes on, but that was my feeling. Let me think.
Well, I don't know what exactly is meant with community model. This, I don't think it means that it's for the public.
Well, at least it means that you can compile it on any other computer and discover, and that's not their goal, this virtual institute people.
I think there's a lot of uncertainty. I don't think we have time to really go into it here. We don't really know.
I would just,
Mike.
Rain said that if you have an idea for a 2-page proposal, just write a draft now in case the program manager comes and says, "What can you do with 100K?" Because
that could happen.
Yep.
Yeah, Nancy, go ahead.
If you're not a civil servant now, who's handling your ROCKE-3D funding?
Well, as I said, Scott's the admin PI, so he will disperse the funding according to the guidelines that I put forth in the ICAR.
Yeah, your guest RA, whose name is briefly stuck on the top of my mind.
Jamil?
What's that?
Jamil,
thank you. Yeah, he's still handling the subcontracting to all the non-civil servants, and but I'm getting the sort of the notices from NSSC when reports and funding is distributed. So it should be, I'm hoping, very smooth and transparent to what it was before, and just have a different name on the paperwork and otherwise identical.
Exactly. Okay. I think I was going to talk about these these two papers I'm working on, but I don't think I'll have much time. This is the paper I've been working on with Eric and a colleague in oceanography at Bangor, Wales. These are the simulations that we've been doing, looking at Archean Earth as an aquaplanet 3.8 billion years ago. And each one of these simulations has different amounts of CO2 and CH4 in some cases, as you can see. And then all of these simulations at the top, the first 3 rows and these first 2 are 1 bar. Then I've done some 500 millibar simulations down to here. And then all of the 250 millibar simulations I did, even up to 100% CO2, ended up being snowball Earth. The 2 with the water belt states, they just didn't reach equilibrium because, as usual, the model crashed before I got to equilibrium there. These are some plots that I won't have much time to go in, but one thing I've been looking at are some papers by John Marshall and people like that, and how they try to understand water belt states. Unfortunately, it's been really hard to compare to previous work because almost everybody used 24-hour days, and I'm not using 24-hour days because there's no way that Earth's rotation rate was 24 hours in the Archean. But what I've seen here is a bunch of different types of water belt states, which I've given names to. Maybe I'll set a precedence here. Narrow water belt states, which are these really narrow things you can see in the upper right. Medium water belt states, so slightly wider, like number 9 and 11 on the left. Wide water belt states, which are just a little bit wider. Super wide water belt states, blah, blah, blah. And the reason part of that is because of the Hadley cells, basically. There's more Hadley cells in these simulations. And depending on the rotation rate, so each pair of simulations, one's 12 hours and one's 18 hours, the Hadley cell difference is making a difference on where the sea ice is limited. And I don't think people have looked at this very carefully. Again, people have looked at 24-hour type things, but I don't think people have looked at an ensemble as large as this, which has made analyzing it and trying to explain it very painful, to be honest. So that's why I have put all of these plots together showing ice coverage, surface temperature, and at the bottom, wind stress. I like the idea, looking at John's papers, he's looking at wind stress, which I like because it's really talking about momentum as a driver. And if you look at other diagnostics, they're often talking about energy. And for me, it seems to me momentum is important when I think about different pressure atmospheres, right? Because not only are we dealing with 1 bar here, we're talking about 500 millibar atmospheres and how they're also kind of distinct from some of the 1 bar atmospheres. So hopefully I'll finish this up here in the next, I don't know, God, when I get my life back in a month or two, get this.
So you said some of the runs are crashing. Is it because of the ice reaching the bottom of the ocean?
250 millibar runs, yeah. 2 of them crashed before they reached equilibrium.
Yeah. Because of the ice reaching the bottom of the ocean.
Yes.
Sorry, what's the difference between the left and right?
One is describing some water belt states, and one on the right is describing other water belt states.
Oh.
So the ones on the right are different kinds of medium water belt states, as we call them. Sorry, I didn't have time to go through this. I don't have enough time to go through all these slides. I'll get to get on the next talk. So, and these are just the normal transport things you see for atmosphere and ocean for the different simulations. I don't have time to go through all these, of course, but that's what I'm working on. And then I have one other paper I'm working on with Rory that I'm very excited about, which I got this very fancy title for. And what's super cool about this, I just mentioned very quickly, is that I had Rory do some dynamical simulations for Earth with 2 kinds of tidal dissipation for Earth over the long term. One using present-day tidal dissipation and just letting that roll out forward in time. And another one using a much more highly dissipative state for the planet. And what we found was on the top are where we use the modern day dissipation, just let it run. And you can see that, of course, insolation is increasing through time. We went all the way up to 3 gigayears into the future. Length of day is changing, of course, because of the tidal dissipation and the moon, receding from the Earth. And these are the temperatures you can see. They're going everything from sort of modern all the way up to 3 billion years ago at 65 degrees at the surface. And the model, amazingly, hasn't crashed. It's always good. See, because the model doesn't like to get hot. It doesn't like to get cold. It doesn't like to get hot, as all of you know. And then on the bottom, I'm showing the same things, but then the big difference is the length of day is quite distinct. So you can see here that we start getting into this slow rotator effect from the day lengths getting quite long. And you can see the temperatures already at a gigayear into the future are already less than they are for the less dissipative state. And you can see that we're getting amazing low temperatures, and even though the insolation is going up like crazy. So even 3 billion years in the future in this highly dissipative state, where you have a 46-day length of day, your global mean surface temperature is only 14 degrees. So this is kind of stuff that's been seen in previous work, but we've never done it quite like this, where we have a dynamical model that shows how you can get the model to work like this.
You might have seen it already. Are these all Planet 2 runs?
Yes. They're all Planet 2 runs with the latest sea ice fixes.
So the difference is the length of day and
Yep. Length of day.
You get the sub-stellar cloud depth? or-
Yes, exactly right. Exactly right. Okay.
Mike, is there an obvious relationship between the gross meridional heat transport with sea ice cover?
There is. We can discuss that later. Thank you. So I'm now going to play a video that Kostas did for us, hopefully. And I'm going to share that screen
Do
here.
you want to switch Kostas and Igor?
Why?
I think that'd be
Oh, do I have
better.
Igor next? No, Igor, you're next. I'm sorry. I screwed up. Thank you for keeping track of the schedule like I asked you to, Tommy.
I thought you wanted to penalize me.
Yes, I should come up here. Okay, here. Hold on here. Let me get this up, and then let me share the screen. Is it, maybe it's already shared? Can you all see Igor's slides online? No.
No.
No. Okay, hold on. Let me try to get Zoom to cooperate. Share. Here we go.
Well, it looks like this thing is also.
Hold on. It'll work. Okay, try again.
Yeah, it's working.
Yes, now again.
Okay,
Good.
go, Igor.
Yeah.
All yours.
Okay, I guess everybody knows me. I'm Igor Aleinov from Columbia University, masochist. So the project I'm working on is this exotic ice snow model. Many of you probably already know it, but I'll just give a quick overview. So this model basically is developed by me, but since it's included in the Mars model, and everybody who is on this page basically is involved in this model. So what is exotic ices model? On Earth, we have only one condensable species, that's water, but that's actually more unusual for a general planet than the usual case. And here are the planets which have more than one condensable species. So Pluto has like a few gases, Titan has H2O and methane, Mars has CO2 and water. Paleo moon, if it had atmosphere, it had CO2, H2O, and actually H2S. That's more recent research shows. So anyway, some model is needed to handle this ices in a like more consistent way than usually is done. And yeah, I was talking to many Mars people how they do two ices at the same time, and mostly they just put it side by side, though they never mention it. So basically, it's kind of hackish. But then again, I think it was Farges, from Farges group talk and recent Mars meeting, and it looks like they're also doing like generalized snow model, so they are ahead of everybody anyway. So anyway, yeah, that's another like motivation thing. So these are just Mars polar caps, and on the left I show shortwave albedo for water and CO2 for different grain sizes. It's from this paper, basically just to show you how different actually albedos are. Like if you go to near infrared, that's from 2 to 6 microns that is shown here. So that basically tells that you have to treat them differently, otherwise you don't get the right picture. And yeah, usually people for Mars, they tune polar caps differently, northern and southern cap, and my goal was like basically to avoid it. And whatever I'm showing in this talk, no special tuning is done for different polar caps. So here's basically what is being done with this model. So the goal is to develop a model which will handle all condensable species in unequal footing and has like they will have their own condensation temperatures and all the physical properties and albedo. And of course, it has to be coupled to the rest of the model, like clouds, if we finally would get CO2 clouds and stuff like that. And so far, it's done only for land surface model, but hopefully it will propagate to other pieces of model, since there are other people on Earth side who are working to use land surface model in different parts of the model. So this is an example how this, basically mostly it was already implemented and works. Right now it works only for water and CO2, but it is generalized in the sense that it's easy to add more ices as needed. There is no restriction to 2 ices, for example. There is just loop over ices. So this is just one cell close to Martian northern pole, and this shows like two seasonal cycles. Gray stuff is CO2 ice, concentration of CO2 ice, and blue stuff is water ice. This actually a particular run had numerical diffusion that was fixed. So it's not slightly unrealistic, but I like to show this slide because it shows how basically CO2 ice can be preserved during the summer months if it is buried under the water ice. So that's kind of like interesting way how things interact. So this is basically our, the rest I will be just showing results for Mars simulations. So first I will show modern Mars and tell a few words also on paleo Mars simulations. So that's how modern Mars is being set up. This on the left is topography. We put water ice cap at the northern pole. That's usually what people do because there is a water cap there. Otherwise, I'm just using modern observed stuff like for topography and albedo, for ground albedo, no, without results, no, and we use interactive CO2, interactive dust model. I wanted to show a little more something that is important for Mars and was neglected recently. You have to use Mars thermal inertia for ground, and apparently it became extremely difficult for me to do this in ROCKE-3D because it has a sophisticated land surface model, and you cannot just set thermal inertia. You have to set what I list here: porosity, grain shape, heat capacity, conductivity for granular material, also for soil gas, amount of hygroscopic water, and a lot of these things are just hardwired in the model. So I had to hack this basically just converting thermal inertia from like what we have for Sun to something more close to Mars, like 284. That's what I'm using, and plot on the right is basically what is measured on Mars. So that's still work to do, but we are close enough. So this basically shows just climate simulations for Mars. On the right, it's also like vertical profiles for 4 seasons. LS, it's solar longitude. It starts from vernal equinox. So on the right is basically a comparison. On the left is what we are modeling, and on the right column is observations. I guess Jan will talk more about this, so I will not take his will not take his topic. But one thing to see is that we don't have much dust uplifted basically higher to the atmosphere, and that shows on temperature profiles on the left that also our temperatures are a little colder when we go further up in the troposphere. So that basically keep in mind. But so this is basically a classical curve that everybody is trying to fix. Now I'm showing CO2 cycle. So gray stuff is observations. It's for Viking 2 side, and red is what we are currently getting. So we're getting pretty good fit, and there is basically no special tuning of different polar caps and everything that people are doing.
It looks like in the polar caps is where you're.
Huh?
It looks like you're still a bit off.
Yeah. Of course, that's still a lot of work to do. But one thing that we are missing is dust in the snow. Right now, we are using just snow aging algorithm, and that's kind of route. So hopefully, we'll get better if when we put dust.
But is this better, do you think, than the original stuff we did a few years ago?
Yeah, a little better, and it's completely different because when you change thermal inertia, this curve is gone. I don't want to spend time with it, but
yeah.
I guess I'm running out. Oh, sorry. Yeah, okay. So I guess I'm running out of time. So this is water cycle, basically just to show you that it's a total amount of water in the atmosphere. So we are getting decent job, but again, too much water on the South Pole. So that probably also could be fixed with better albedo approximation. So this is snowpack. The top is snow thickness. The bottom is concentration of CO2 and water in the ice. It basically shows just how things switch between the seasons. And since I'm out of time, I guess I will not talk about this more. This is albedo. Just show you a picture. Again, you can see that basically albedo is kind of different from the northern in northern hemisphere and southern hemisphere for snow because like of different aging, I guess, things. But it's also can be improved with when we include dust. So and now I wanted to show you something what I did for paleo Mars. That's basically what I was using: 60 obliquity, 1 bar of CO2, and paleo insulation. I set uniform snow all over the atmosphere, all over the land, very thin snow. And this is the interesting result I want to show that I'm getting. Actually, when I use interactive dust, I have huge amount of dust in the atmosphere. So on the left, I'm showing atmospheric optical depth, and on the right, I'm showing actually the mean surface pressure, and it's falling. So we actually losing atmosphere because of these dust storms. So it's basically global dimming due to this storms freezing out the atmosphere on ancient Mars. I don't know if anybody have seen such things before, and I'm not sure if it's correct, but I cannot convince myself that it's completely wrong. So this is basically that cycle on the top, like huge amount of dust in the atmosphere. And at the bottom, I'm showing the vertical profile of the, temperatures below CO2 freezing. One thing we are missing is so-called wet removal due to CO2 condensation. So I was thinking maybe that's a problem, but there isn't much CO2 condensation. At least I doubt that you would remove a lot of dust by this. So basically, this other region, yeah, and that's all what basically I want to show you. This is just snowpack for these simulations, just to show you how it is. And this is when we disable snow dust. So it looks more like modern Mars, much less snow. And I guess I already.
Yeah. Okay. Thank you, Igor. That was good. We'll have to move on to the next talk, but as I say to everybody, please sign up for one of the group meeting talks. I mean, we meet every 2 weeks, and it's great if people want to come and talk about the research. You had so much stuff here, Igor, that it would be great to see that. So let's move on to this thing. Share that. Hopefully that works. And then we're going to hear Kostas's voice from Beyond the Blue, hopefully.
So I guess it doesn't need.
He doesn't need that. No, it just plays on its own. Let's see. Let's hope.
Good afternoon, everybody. First of all, I'm sorry I'm not there. I hope you're having a great time. And I'm going to present you the current results we have in a project with Sonny Harman which is funded by NASA Rose's Habitable Worlds. We are a little over a year into the project and we are doing some pretty good progress. So I'm going to be discussing about the way we are creating simulations and how things are going, but goals of the project, which are essentially to take a model Earth twin and vary key atmospheric parameters using ROCKE-3D and see what happens with climate. And we are very much interested in doing that by looking into short-lived forces like gas phase chemistry and aerosols, and see how these are being affected, not just climate parameters, as is typically done. The parameter space is always the biggest problem. So we'll vary eccentricity, obliquity, rotation rate, and nitrogen abundance, and which will also affect pressure. And you can see the values here. I'm not going to go into details there. And then after we have a very good sense of our parameter space, we will do some Latin hypercube simulations to be able to understand the system even better. For the control simulation, this is where we spent practically all of the first year of the project. So we want to combine two ROCKE-3D version 2 configurations. Both have Socrates radiation and the dynamic ocean. The difference is the atmospheric composition and the level of generalization. So in ROCKE-3D, we had a generalized planet having an anoxic atmosphere, this simulation over here. And then we had an oxygen-rich atmosphere, which is this one, which on purpose was designed to resemble the present-day Earth as much as possible. So what we did is that we took the oxygen-rich atmosphere and took the generalized components in it and created a new simulation. We discovered a few things along the way. That's a topic of a different discussion. And we also added some passive tracers in there, which we have not analyzed yet, but we're planning to. Now, one of the things that we are doing and we're thinking, one thing is that we are trying to do proper vegetation. You know, you are going to be affecting the rotation rate, and that means that nights will become longer, or much longer, or perpetual even, for the tidal lock cases, and that should affect vegetation. So first, for rotators that are not tidally locked, we started with a vegetation cover that is just uniform across latitudes. We then tried to do that more smart by creating some configurations, some climatological configurations, and then using them to create a vegetation cover based on scripts that Nancy gave us. And that works well, so probably we will go for that. Still need to decide what to do with the slow rotators, because the climatology does not have diurnal variability. So we need to see when vegetation essentially dies out. And we have removed the land ice, so we can allow ice to develop anywhere it likes, but since the model is not simulating land ice, everything is going to be taken over by snow, essentially. And then we played around with the maximum allowed snow depth, which is the three parameters inside the model, and we saw that the total or the global mean snow thickness is changing a lot by the change of this parameter, but the result climatology does not change much, because essentially having a snowpack of like 10 meters or 100 meters will not affect things like albedo much, so we don't expect any big changes there. For the ocean, that is the tricky part. We wanted to make it more generalizable, so we used the bathtub ocean, and we tried either with or without continental shelves, so either directly going deep or with one grid box being a little bit shallower. We haven't decided yet which one to use, because we're still getting some crashes in some weird configurations, but we'll see about that. We tried both the constant and the simple mesoscale diffusivity, and which was, by accident and practice for a generalized case with constant, and that's what we will be moving forward. And for the most part, simulations reach equilibrium after 150 years, so we don't have to worry too much about doing very, very long simulations. The parameter space that we explored, eccentricity, top left, behaves as expected. You see that for most eccentricity values, the surface air temperature is simulated, global mean is simulated to be very similar with present-day Earth. This is year 0, this is year 200, starting from some initial conditions. All configurations start to the exact same initial conditions. And then the eccentricity, when it goes to 0.15 or 0.2, it starts to create a much hotter planet on the global mean. That's because it goes very close to the star, and that affects the short time of period that is very close to the star appears to be affecting the global mean quite a lot. So it looks like the yellow here, the 0.1 eccentricity, is the threshold. We're still exploring the details here. For the obliquity, we mostly had no problems with that, other than some technicalities here and there. There is a technical issue, the 90 degrees obliquity, which makes the model crash. We will have to work on that. We haven't figured it out yet. More slides to come in a minute. The rotation rate, everything is crashing. So we're still trying to see what's going on here. For the very fast rotator, which is essentially half the duration of the Earth day, so it rotates twice as fast, we get a very cold planet that crashes eventually. And then for the 1/3 rotation rate, so 1/3 duration day. What am I saying? Three times Earth means that the planet rotates 1/3 slower, and so 3 times smaller days, longer days. So the smaller more that we get is because of the fast rotating gyre in the ocean that essentially empties completely grid cell from ocean water in a time step, which is different from the standard smaller more that people might have been seeing with freezing to the bottom. And then other runs are still crashing, so this gives us a hard time. And with the N2 abundance, we have the wrong setup, so we will discuss it. For the obliquity, you see that the surface air temperature here, and look at the equilibrated values. So the value of 0 and 180 fall exactly on top of each other. The value of 30 and 150 are also here, together with the value of, they are here, 30 and 150. And then the value of 120 and 60 are right there. So perfect symmetry, that's really great. The model does what it needs to do. This is Earth right in the middle between those two, and F15 is very close to 0. So it looks like there is a fast transitional regime between 15 and 30, and Earth falls right in the middle there. That's something to keep in mind. The ocean ice thickness for the high obliquities is increasing very, very much, and there is nowhere near equilibrium yet. And it appears that the values between 23 and 30 have a very large difference here. So something very big happens in that transitional regime, and Earth looks much more than the lowest obliquity counterparts, highest obliquity counterparts. So we have to see why the 15, which is here, I have them backwards. So the 15, which is here, and the 23 and the 30, why there is such a huge gap here. And that's the ocean ice thickness. We would not see the same in the ocean ice fraction. So we have to extend those runs and see how the fraction would go. The troposphere pressure is also changing quite a bit, and also the atmospheric water vapor column, which is also dependent on temperature. So you see that these lines here that are very hot produce much more water in the atmosphere, which is expected. The clouds are interesting as well. You see that the low level of cloudiness is affected quite a bit depending on obliquity. That goes from 29.5 to up to 35, so that's something like 20% change. Precipitation changes a lot as well. Earth again is somewhere here in the middle, and there are extreme cases both above and below it. And it's also interesting that there are some cases that are having an overshoot and then equilibrate, or others that equilibrate more smoothly. And here's another overshoot if you follow the red and the blue. So maybe there are some interesting physics happening at the equilibration time to study. High-level cloudiness looks backwards, or actually mixed compared to the low-level clouds. So you see that this line here is down there, but then the next line is the red and the blues, which are up here. So there is some very interesting mix to see in this case. And also interesting, the very soil water that is showing to be Earth at the extreme high case, and then the 15, and then all other simulations, regardless of whether they're the zeros or the 60s, are right there. So Earth again looks to be in a unique location here. And that is a pattern that we do not see in the vegetated soil. So that's also interesting. Not it. It looks like obliquity has something there for us to explore, and we have to debug the rest of the simulations we have, and start the simulations again, and then turn on chemistry and see what happens. Thank you. Sorry again for not being there. If you have any questions, feel free to reach out to me, and I'm happy to discuss about it. Thanks.
Okay, great. Well, we can move on to Kevin's talk. Kevin, are you going to talk, or is it going to be Vasuda?
I'm going to talk.
Okay, he's alive. Good to hear.
All
All right.
I'm still alive. Yep, not dead yet. All right, let me share my screen here.
Yeah, or you can do it there if you want. You want to share your screen?
Yeah, I can just do that if that's all right.
Go for it. That's good. Go for it.
All right. I think you should be able to see it now. Is that true?
It's still thinking. Hold on.
There, maybe.
There it is. We see your slides. It's not in full screen, but we see it.
Okay, great. Yeah, I don't know how to get it full screen here on this thing.
Now we lost your audio.
No, do you have my audio?
Yeah, we do. It came back. I don't know what happened.
Okay, brilliant. Yep, that was a weird glitch. I don't know what happened either. All right, so here at UAlbany, our team is working mainly on developing a Bayesian machine learning framework for predicting atmospheric absorption spectra based on planetary parameters. So I'll just give a quick general overview of what we're doing. We're basically designing a machine learning system that will take atmospheric spectra from solar system worlds such as Venus, Earth, Mars, and Titan, and also synthetic GCM modeled spectra, and train it so that given planetary parameters, we can predict what the spectrum should be. So there are several challenges here. And one of the benefits of this is once we are able to predict atmospheric spectra based on planetary parameters, if you have a machine learning system that can do this quickly, then given data consisting of an atmospheric spectrum, you can use the prediction, the difference between the actual data and the prediction, to compute a likelihood function, which you can use in a Bayesian calculation to estimate planetary parameters from data. So that's one of the ultimate goals as well. And a few questions come up. First, how do you best model the atmospheric absorption spectra in a machine learning system? You need some kind of parameterized mathematical model to be able to generate the prediction. So one of the simplest things you can do is come up with maybe here on the left, you have a very crude six binning with unequal bin widths. That's not very helpful. You might go with a higher number of bin widths. In this case, on the right, I have a histogram with smaller bins showing a little more detail. In this case, 20 spectral bins. And the question is this going to be good enough or not? And so have been working to try to decide what type of binning we should use. Are bins really the best way to go? You could use a continuous model as well, which might be more helpful. Some of continuous functions like wavelets or something like that. You can produce these using techniques like principal components analysis, which is really way too artificial and gives you non-physical results. A lot of people like to suggest independent component analysis, which is not a technique, it's a class of techniques. And out of all of those techniques, probably the most useful one without excessive prior information would be non-negative matrix factorization. So we're looking into that as well. Ideally, what would be nice is, especially with the fact that we're producing simulations, if you could actually model this as a physical sum of molecular spectra, so that the simulation actually tells you what the carbon dioxide spectrum looks like, what the oxygen spectrum looks like, what the nitrogen spectrum looks like, and add them together to give you the full spectrum of the planet. However, that presupposes that you don't have interactions that give you nonlinear effects, so that's difficult too. And then the other question, maybe the bigger one, is how do you model predictions in a large planetary parameter space? We've been starting out with one parameter. I think we're up to 3 parameters at this point. But in our earlier discussions, we were looking at on the order of 30 planetary parameters. And so we need some kind of parameterized mathematical model that can work in high dimensional spaces. 30, how high? 30 dimensions is a good place to aim. To start out, we started with the spline model. Simple to use. It's too simplistic, though. It works well in 1 dimension. It doesn't work well in 3, and the number of parameters blows up very quickly as you add dimensions. So we've also moved to Gaussian processes, which are more complicated. And it's not exactly clear yet how to handle the very high dimensions. We've got them working in 2 and 3 dimensions at this point. So I'll show you a quick example of what happens with spectra that have very small numbers of bins. We're looking at only 6 bins or so, and we're using splines to see how well this works, just in 1 dimension, so 1 planetary parameter. This has been presented at the MaxEnt 2024 meeting and has been published in the proceedings there. So in a first pass, we only consider 1 planetary parameter. The spectral bin heights are then modeled as a piecewise cubic Hermite interpolating polynomial, which is a spline curve. And we only considered 6 bins for the spectrum. So we created synthetic data. These functions on the left here are the actual functions that the spectral bins follow. So this is the truth. And we then picked several data points. Here we have 6 data points picked out, which each datum is basically a 6-bin spectrum. So here at like 0.05 or 0.5 for the parameter x, we have 1 spectrum. We have another one at about 0.25, and or 0.3, 0.35, and so on. So with these 6 data points, we want to be able to see how well we can estimate these actual functions. And so we use a Gaussian likelihood here and use the nested sampling algorithm. And given those 6 data points, this is what the predictions are for the 6 different bins. And the actual curves are drawn here. The wide areas show the uncertainties that are coming up from the various possible spline, the probability density function for the spline parameters. So you can see the regions of high uncertainty. You can also calculate this is the sum of the squared residuals, and this is the sum of squared deviations, which are then actually for a Gaussian process would be proportional to the entropy, and suggest that where this is high are best places to get more data. So we realized, well, we'll need more data at these points. So once the planetary parameter space is estimated, we've got some samples from there, some simulations. We can figure out where we could use simulations to make the machine learning system better. So this is with adding one data point here at the 0.85 position. You can see the uncertainties drop around 0.85, and then adding two more data points brings things way down. And now we basically have 9 data points here, and that we're able to estimate these functions pretty well. So that's basically what we're working on. Gaussian processes look more promising. They're going to work better in higher dimensions. We have one last thing, one additional effort that actually came from another project. We are working on developing an analytic installation model of close-in orbiting planets. If a planet is close to its host star, and especially when the host star is large, the parallel ray approximation breaks down, and you don't just have one day side and one night side. You actually have several different illumination zones. So here's the geometry of this. We get a fully lit zone here on this part of the planet on the right. The planet's on the right, the star's on the left, and on the left side of the planet facing the sun, you get a fully illuminated zone from which anywhere at that point of the planet you can see the full disk of the star. In the next zone over, we call the penumbral zone. This is the region where it looks like the star is starting to set, but less than 50% of the star is below the horizon, so you can still see more than 50% of the disk of the star. The adumbral zone here is where more than 50% of the star is below the horizon, and then you have the unilluminated zone. Why is this important? Because we've noted in our past work that estimating planetary parameters for close-in orbiting planets reveals unusually high temperatures. This actually, let me see. Oh, I can't change to that because of the way I'm casting my screen. So, because you can see more than 50% of the planet's illuminated. So when the planet's in the new phase, you can actually see some of the light. You can see a ring of light around the planet when you're doing photometry. That's not accounted for in the current illumination models. So how are we going to handle this analytically? Basically, for each zone, you have to integrate over the surface area of the star, the visible surface area of the star. You have to integrate the flux, the incoming flux. So this is a good bit of mathematics. Here's the basic integral. You've got a dot product for the amount of light coming off the star. You've got a dot product for the light coming in to the planet, and 1 over r squared, basically. And then for each of the 3 illumination zones, we get different limits of integration. So the fully lit zone is seen up here in A. That's what the star looks like. In C, that's the penumbral zone where the star appears that part of it's occluded by the horizon. The adumbral zone, more of it's occluded by the horizon, and so on. So what do these integrals look like? They look like this one at the bottom, if the AI assistant will go away. So this is an integral that has 5 terms in it. So you can break this into 5 double integrals. For each region of the 3 zones, there's basically 5 regions to integrate over. This just comes down to 50 integrals to solve. So 25 double integrals. So, and some of these limits of integration are, at least fortunately, they're linear. So that helps. So we expect to be able to solve that. I'm going to stop sharing and go back to sharing in just a moment. I'll show you the other thing I want to show here. Higher screen. Yes, do it that way. And now I can hop over to my other thing. This is from right, so this is I can see it on your screen. This is basically a simulation up here on the upper right of Kepler 91b. And you can see that about 70% of the planets is illuminated. And actually in the new phase, you actually see a ring of light. This is what's leading to an overestimation of temperatures. And in fact, there was a paper on the archive just last week on this, on 5 close-in orbiting planets they're estimating physically unreasonable temperatures. And this is basically why the systems are trying to describe this ring of light, and it's basically doing so with infrared light being emitted from the night side, which makes the planet hotter. And so we've got some biases coming in because we're not modeling installation properly. So hopefully we'll correct that. And that's basically it. Thank you.
Okay, thank you, Kevin. We have time for maybe a quick question or two, if anybody has anything they want to share or ask about.
Can I ask?
Yeah.
One other dimensionality reduction you could do would be like a latent space with an autoencoder, but I'm wondering if you're thinking of something binned or Gaussian process because you're thinking of observables, because a spectrometer would have some spectral width.
Right. Oh, that's a good thought though. Yeah, thank you. We'll consider that. Yeah, at this point, any suggestion would be good. 30 dimensions is rather daunting.
Yeah.
Yeah, the idea was to put actually some of this illumination stuff into ROCKE-3D because we think that there might be some cases where close-in planets around M dwarfs might have this extra illumination. We should take it into account in the model. And it's actually something that Gary Russell even brought up last year when I told him about this. He goes, always wondered about that. And also, refraction of light in the polar regions, we don't get the right temperatures. And I've always wondered if that was because of stuff like this. So this has some good application to the model. So, I mean, we've had a non-analytical formulation since Jen's thesis, more or less, right? One of his former graduate students. But
Yeah, Jen Carter's work.
Right. And we really need an analytical expression to put into the model. So that's what part of the driver of this is. And it costs, of course, will be shared with people around the world using these sorts of, these are the models he's talking about are more like hot Jupiter models, but they're getting things wrong because of this extra illumination. So it's exciting stuff and getting back to it, which is really good.
Yeah, we hope to be done with that, have it done by the end of the semester. So that's the goal.
Right on. Okay, good. Thank you so much, Kevin.
All right, thank you.
Find Robert's presentation, which I had up before, and then I misplaced it, so it's fine back to here. Good. All right. So let's see. I don't use this so much.
Just hit play.
Just hit play, okay. And then I have to share my screen. Oh, no, it doesn't let me share the screen.
Oh, you have to share it before.
So just hit, okay, so let's see, go to this, share, I guess.
The keynote with
this one.
Yes.
He knows what he's doing. That's good.
It's not my first rodeo.
Okay. You want to take the pointer?
Will it let me advance the slide?
I hope so. We'll find out. Okay,
Now you.
Okay, I'll let you can sit here. If you like.
Thanks. So I'm an exoplanet wannabe, and so thank you for tolerating me. Advance. So a lot of what I'm like an atmospheric physicist guy with experience in radiation and clouds primarily. And so one of the things that I've been struck by recently, one of the things that's come up, it's changed in the field for the last, 5 years, let's say 8 years, is the shift from calculation to idealization. And so when I think of all the things that I know about how radiation sculpts the circulation, the structure of the atmosphere, how the clouds interact and heat and cool the atmosphere, all of that comes from calculations with dynamical models and full complexity radiative transfer. Calculations, even if sometimes we'll do simple problems like aquaplanets. And to my mind, the first paper that has taken this new approach, but there's been a whole slew of them, came out in 2018. A bunch of them came out in 2020 and 2021. Daniel Cole, Tim Cronin, Nader Givenchy, people like this, right? And so Nader Givenchy, Daniel Cole, you guys will know, but yes. These other people are working more on Earth's atmosphere. These are pencil and paper models. I'm going to walk you through one that we've done that have explained a whole bunch of stuff, like why the radiative cooling is roughly 2 Kelvin per day through the depth of the tropical atmosphere. It's not obvious why that would be if you think about it in a gray radiation way. Why the radiation emitted by the Earth is the OLR is the outgoing long wave radiation is linear in surface temperature when OLR goes to sigma to the fourth. Two that I'm going to bring up here, and they're relevant for Kostas' talk, are why the tropopause temperature is nearly constant, and how the rate of change of rainfall with surface temperature. What does that depend on? So the example I'm going to show you is what we call the hydrological sensitivity. So that is to say the D rainfall, D surface temperature on Earth. And well, okay, sorry, I'm getting ahead of myself. I'm going to show you two sort of key idealizations that get made. One of them I was talking about with Brian earlier. One of them is if you ask yourself, what's the flux at the top of the atmosphere? You solve Schwarzschild's equations, right, from 1905. And you say there's a boundary term, and then there's some integral term that accumulates the contributions through the depth of the troposphere and attenuates them according to the optical depth at the top of the atmosphere. And if you rewrite that in pressure coordinates, you get a weighting or a contribution function in pressure coordinates. And that weighting function goes as tau e to the minus tau, and that has a maximum at tau equals 1, right? And this is because you're writing it in pressure coordinates. And so we often say, like, we have an emission pressure or an emission tau, and that comes from tau equals 1. And the jump from saying, well, we have this weighting function which you can draw, and it maximizes at tau equals 1, to saying, I'm going to use a delta function at tau equals 1 that's obviously conceptually small. It's not really true. I've been working through this for a review paper, but because optical depth varies by orders of magnitudes, 5, 4, 5, 6 decades for most of our greenhouse gases, this as an approximation, thinking about a delta function for emission temperature or pressure works well. There's two corollaries to that. One of them is about local radiative cooling. And so that I will rely on for the example I'm going to show you. And that's basically said that is equivalent at some level to saying that cooling in the atmosphere is dominated by what's called cooling to space. So that is, you can reformulate the net heating of the entire atmosphere as being, exchanges with the atmosphere above you, below you, with the space and with surface. Only one of those has a very different surface temperature. So and that's space, which is 0, and U, which is whatever temperature you are. So local radiative cooling is well approximated by so-called cooling to space. For condensable species, and I never think about these covariations, I'm so intrigued by that. When you have a condensable greenhouse gas, one of the implications that was originally identified in the 20s is that the spectral OLR at parts of the atmosphere where you're already optically thick due to your condensable, that spectral OLR is fixed because, basically because the concentration of the condensate is fixed in temperature. And so you reach tau equals 1 for some set of wave numbers for some concentration, and that concentration moves up and down. It moves it's constant with temperature. The big insight that's come about is that you can take this mess of absorption material, of absorption spectra. So here, this is from a paper by Andrew Williams, who's a sort of a wayward guy that kind of hangs around my group a fair amount these days. And so you can look at the absorption by the lines. You can look at the absorption by the continuum. Here we're using the MTCKD continuum. You can look at the absorption by carbon dioxide. And you can say, geez, that's a lot. This is why we use correlated K or any other technique. And the insight that's come about and what's led to all this progress is the idea first that you can, of course, add these things up. And then you can simplify, or then you could coarse grain them would be one way to think about this. And then you could draw simple analytic bits. So one of them would be here a triangle. And that's essentially saying that the absorption coefficient varies in some very predictable way in wave number. And whether or not it's actually, captures the details of the behavior, even the, it's not perfectly quantitative, but it lets you write an analytical integral. And you can do that for water vapor somewhat more, it takes more fussing, let's just say it like that. Okay, so we applied this to hydrological sensitivity. And that is, so the way that I think about that is, so we, first we say that the in the paper, it says hydrological sensitivity we're going to address by looking at how atmospheric radiative cooling changes with temperature. So that's essentially saying that the latent or the sensible heating at the surface doesn't matter much. Its change doesn't matter much with surface temperature. You write the total flux divergence as this cooling to space term. This is the cooling to space term. You take its derivative, you use your calculus, and then you invoke this idea of so-called Simpson's rule, which says that the spectral OLR is constant in temperature. And so that gives you this very simple first expression. Okay, so that's Simpson's law, tells you why you can cancel that term. And so this just tells you that you are changing the spectral emissivity, that the hydrological sensitivity comes from regions where you are able to change the spectral emissivity with temperature. So that means because emissivity is bounded by 0 when it's optically thin and 1 when it's optically thick, and it doesn't care if it gets optically thicker, this tells you that there's going to be a finite part of the spectral region that is going to contribute to the hydrological sensitivity. We wrote things out. You can see that, again, because of Simpson's law, that this basically relates to the change in the liquid water path, the integrated condensate amount through the depth of your atmosphere. There's a physical picture here that I'll just sketch out for you. I mean, there's a paper that came out about a year ago that you can look at that's down here. One way to think about it is that a whole bunch of the atmosphere in the absorbing part,
Yes.
Oh, but you can't see it. All the optically thick parts, so for those of you in radio land, it's the wings where the black lines are. All the optically thick parts, their OLR never changes. Their cooling never changes. But as you increase the surface temperature, you add a piece of the atmosphere that transitions from optically thin to optically thick. All the cooling, the extra cooling with surface, you increase surface temperature, you increase water vapor burden. A different part of the spectrum becomes optically thick. That's where the cooling arises. That's where your hydrological sensitivity comes from. So it's the spectral properties of water vapor that matter, and not really at some level Clausius Clapeyron at all. You can incorporate the continuum, the water vapor continuum, which flattens out this like ditch. You can add CO2, which takes a bite out of the cooling. All that stuff is possible. What it tells you is that hydrological sensitivity, maybe focus on the orange lines here at the bottom. What it tells you is that hydrological sensitivity for Earth's atmosphere, water vapor condensable, 1 bar, has a peak at about 295, maybe 300 Kelvin. So in other words, it ought to rain more and more until you get to about 300 Kelvin, and then it ought to rain less and less. And in fact, that's what David Bonin and Tapio Schneider found in, and actually, I guess this is Eric Wolf's work here, this line with Exochem 4. So our calculation with all the bells and whistles is this black thing. One of the things you have to do in order to get to this calculation is tie together the carbon dioxide concentration and the surface temperature. That's what we call in climate world climate sensitivity. So it's,
why do you think yours is falling off faster than this is?
because he's using a whole GCM and we're using pencil and paper. Would be the first argument.
So there's some other secondary effects.
Yeah, I mean, I don't really know. Our spectroscopy is fairly heavily idealized.
It's not great.
Sorry,
it's not a great.
No. It's this full spectral
okay.
model. It's
right.
this spectral model. Sorry, it's this spectral model. It's these dashed lines. That's our spectroscopy. Is these dashed lines. I mean, it's not exactly those dashed lines, but it's close. Anyway. So why am I telling you this? Because I think this is what the next slide says. Why am I telling you this? Because I think this is one example. In my own group, there's probably at this point 5 such examples. In the larger community, there might be 15 examples of people trying to do this kind of work. And One of the interesting things that's come up recently, for example, is a theory for the tropopause temperature. Why can't we get to my last slide? There is the tropopause temperature, and the idea here, and this has its roots in theories for cloud feedbacks from the 90s, but it has more recent roots from work by David Brahms and Jake Seeley on the fixed tropopause temperature. The idea here is essentially that the tropopause is set, the place where the stratification happens is set by the maximum absorption coefficient of water vapor. Because if water vapor condenses, it means that as you get colder and colder, you are still effective at cooling until you run out of very optically thick material. And then you're subject to the heating from ozone. And so that's, this is a paper by Brett McKim. I'm not on this, but I'm just pointing out to you that this is the kind of reasoning that we are doing. And so when I see Kostas, or I saw this paper that was described in one of your group meetings, Eric Wolf explaining how they work through this huge parameter space of planetary parameters, or this work that Kostas is doing, or some of this other work that we're hearing about earlier today. I think maybe there's a way to use what we, pencil and paper, to understand what kinds of structures are possible before you run an entire GCM. Of course, it's not the whole story. It just would give you a little bit of guidance to understanding what parts of the parameter space are worth exploring and what not. And I don't know how, but, or it might tell you something, for example, about the condensate cycling rate, as a function of temperature, right? How does that depend? Because as I was showing you on Earth, that's entirely dependent on the spectral properties of water vapor, but on Titan, I bet it's the spectral properties. So I guess methane, you can tell me, but anyway, the point is, I think there's an opportunity here to use this pencil and paper reasoning that we are developing kind of rapidly for Earth's atmosphere to think about constraining the possibilities for especially rocky exoplanets. That's the pitch. And thank you for tolerating me.
Awesome. Thank you so much, Robert. That was good. So I'm thinking about other parts of the parameter space. There's some work by Colin Goldblatt and others looking at methane and how that can do some cooling instead of heating in parts of the atmosphere. And then,
and Eric saw that, right? Is my memory. Oh, hey, yes. Nancy, did you have a question?
Oh, yeah. This is really intriguing. And so would this have any implications for how you calculate the contribution of the surface versus clouds or the atmosphere to the planetary albedo? Because Donahoe and Battisti came out with this paper that gave, some method, and I implement their equations, and I tried to apply them to some ROCKE-3D simulations with different stellar types. And I was getting this trend of departures from the totals with the stellar temperature. And I was wondering if I made an error in my arithmetic or what. So, but I'm wondering, maybe there's some assumptions about.
There's been relatively little work in the shortwave that I'm aware of. There's one place looking at clear sky. It's a lot easier to do the clear sky. I have a student who's now, or a former PhD student who fled to France, who's now who's worked through how clouds contribute to the OLR in an interesting way. It turns out that, I have been doing clouds my whole thing. They're kind of not that important. It's mostly the water vapor that's important in the OLR, as it turns out. No, but there's an opportunity to work that through for sure.
Okay, I will bug you later.
Yeah, please.
Okay, great.
You have time for maybe one more quick question? Yeah, go ahead. Make it quick.
I think these energetic perspectives have a lot of input. Like the whole theory of the habitable zone, has been based on these weathering arguments that as you go farther and farther, you increase CO2 and your precipitation changes, your weathering changes, but there is just, this is like a year ago, like Pierre Humber, Graham, they have these papers showing, if you have a dense CO2 atmosphere in no installation, the precipitation sensitivity is different than modern Earth. And so I think these theoretical arguments can there's still room for them in the exoplanet world, because like the core concepts of habitability are still, you know, like it's probably been thought about wrong.
Oh, interesting. I would say the pitch for the one reason I wanted to show Andrew Williams' work is that, so I also have a radiation code. That just Gavin was very adamant about not adapting because, well, I guess because GIS has its own long history of doing this, but we've built that that simplified radiation into my code. So we are coupling that to CESM. And you know, in other words, the link between simplified radiation and dynamics is, I think, open to exploration. And that could wind up being really, like, I have a bunch of questions I want to ask in Earth's atmosphere, but I think it could wind up being pretty cool in other atmospheres as well.
Okay, well, let's take a break here and we'll come back at 3:15 sharp, East Coast time, of course. Thank you again, Robert. Okay, our next speaker up is Rakesh Mogul from Cal Poly Pomona, who I've been working with for a few years on exciting new results from Pioneer Venus data. So go for it, Rakesh.
Hi, thanks for having me. Thanks, Mike, for inviting me. And on the bottom of my title slide here are my co-authors, with a shout out to them. So yeah, I'm here to talk to you about results from the Pioneer Venus Large Probe. So just a little primer here. The Pioneer Venus Large Probe separated from the Pioneer Venus Multi-Probe in 1978, and then dropped down to the surface in December that year and impacted the surface about 54 minutes later. And on board the PVLP were several instruments, two of which were the Large Probe Neutral Mass Spectrometer and the Large Probe Gas Chromatograph. Both of those measured atmospheric gas abundances. And this talk is mostly about this instrument over here, the Large Probe Neutral Mass Spectrometer, which is also known as the LNMS. So this LNMS was electron ionization mass spectrometer that operated at 3 different electron ionization energies and acquired roughly 45 spectra throughout the descent. So how the descent profile went forward is that spectra of the atmosphere were actually collected beginning at 64 kilometers. But then between 50 and 25 kilometers, the LNMS experienced a temporary clog of the atmospheric intake inlets. And this was the result of inadvertent capture of cloud aerosols. But then from 25 kilometers down to the surface, this clog cleared out and atmospheric gases were again intaked. So this entire profile is maybe better visualized in this cartoon drawing over here. So on the left, I have kind of a cartoon drawing of the LNMS, which had a very, very narrow opening in the intake inlets. So between 64 and 51 kilometers, atmospheric gases were collected. But then approximately between 51 and 40 kilometers, a bunch of aerosols are captured on and inside the inlets, and then gas intake decreased. Then what's really cool is that as this probe descended through the hotter subcloud atmosphere, these aerosol species began to thermally decompose. And so as a result of this thermal decomposition products, several gases relating to the aerosol composition were released into the LNMS. So this is consistent with what was found in the original investigations in 1980 at Hoffmann. And then we began to reanalyze this data beginning in 2021. And we actually confirmed some of their findings in 2023 in an Icarus paper. But what we found is that there's actually more going on here. And that as this probe went from 25 kilometers down to the surface, it turned out the inlets actually heated up a lot more. And it turns out that, yes, gas intake then resumed, as I indicated in a previous slide. But what we suggested is that there are remnants of the aerosol that remain inside the inlets. And as the inlets got even hotter, the decomposition continued and other compounds released into the LNMS. So in other words, in this archive data set for 45 years plus, there was uncharacterized data relating to both atmospheric gases and the aerosol composition. And we've actually used this information to get new results. So to kind of break this apart, we've actually broke apart the data into 2 sets. Both of the major atmospheric gases, such as CO2 and N2, which we actually were able to characterize. But also there are a number of aerosol decomposition products, and this included SO2, SO3, water, O2, as well as FeO plus, which I'll get to in a little bit. So at first, I just want to go back and talk about the CO2 results, which are actually really interesting. This was published in 2023, so it's not new results, but there's a new finding over here. So what we were able to do using a bunch of cool information we found in project reports and in notebooks, we were able to actually convert ion counts for CO2 into density or kilograms per meter cubed. And then we expressed this in this plot as a percent of the atmospheric density. So the LNMS values are the red plots over here. And then this value over here, this is what the expected CO2 density should be. So you can see we actually get a nice real straight line, but there's lots of divots, if you will, or pits. And so if we plot this CO2 profile against the particle extinction coefficients measured by Venera 13 and 14 and the Pioneer Venus Large Probe, what we see here is that, yes, there was a major clog between 51 and 25 kilometers where CO2 intake decreased by about 6,000 fold. This plot showing that the drop in CO2 correlates in terms of altitude where the extinction coefficients for these particles are highest. And that supports the assertion that this instrument experienced inadvertent capture of cloud aerosols, which caused this major clog. Then once the clog cleared out around 25 kilometers, we also see a bunch of drops in CO2 density. And so what we've hypothesized here is that the instrument also experienced partial clogs of the inlets at approximately 15 kilometers, 10 kilometers, and 3 kilometers. Now, why that's interesting in terms of present day analysis is that just this last year, Kulkarni et al. Published a reanalysis of Venera 13 radiance data. And what they have evidence for is a particulate layer at around 3.5 to 5 kilometers, which correlates to where this species over here, or at least this increase in CO2, perhaps due to the release of isobaric species into the LMS, suggested the presence of a particle layer. And then through chemical modeling, Voigt et al. In 2025 also say that there's potential sulfate hazes at 15, 9.5, and 2.4 kilometers, which correlate really, really well with this CO2 profile. So I thought that's really interesting, and I want to present that here. Next, we've also been working with nitrogen, which is also a major atmospheric gas, but not nearly as abundant as CO2. And what we see here on the right, red and green, are the LNMS data. And I've plotted that against other measurements taken in situ, as well as from orbit from other spacecraft. So first of all, the value we get from the clouds between 59 and 51 kilometers was roughly 5.2 volume percent. But then down here in the deep lower atmosphere, the DLA, we get a very different value. This is less than 15 kilometers. We get about 2.5 volume percent. So why is this interesting? First of all, these LNMS measurements represent the first measurements of N2 in the deep lower atmosphere. There's really been no reported measurements down really low. And then what we see is a 2.1-fold difference between measurements in the deep lower atmosphere and the clouds. And so overall, this shows us that N2 is actually quite well mixed below 15 kilometers, but it's not well mixed above 15 kilometers. And moreover, we see that the LMS measurements are consistent with most other Venus measurements, including the LGC, the gas chromatograph on the same probe, gas chromatographs on Venera 9, 10, and 12, and mass spectrometers on Venera 11 and 12. And what I don't have listed here was also the messenger measurements up on top. So that was CO2, that's N2. That leads us then into the isotopic composition for N2. This is a very, very short slide over here, but what we were able to get is the isotopic composition for N2 in the clouds. And the value is shown over here in terms of delta N15. And so this is the Venus value over here. So I'm going to keep this real short and that to say that this represents the first constrained isotopic composition for N2 that's been reported, and that Venus's clouds fall in between solar wind and Earth's nitrogen. However, there's further interpretation of this actual result are needed. We've not really gone into the cosmochemistry or planetary chemistry regarding why this value is between these two constraints, but more interpretations are needed. So from here, I then talk about some aerosol decomposition products. So on the left here, I've got the SO2 profile, and this is the apparent mixing ratio from the LMS. And note that this is a log scale because this is really important. So the LNMS value, which is highlighted over here, is compared to the LGC and a bunch of other measurements that are summarized in this blue box. And as you can see that the LNMS values are super high compared to everybody else, except for the LGC values. So this is the first indication that maybe this SO2 measured by the LNMS was not an atmospheric gas, but something else. Similarly, we see something very comparable with water. So most measurements of water vapor in Venus' atmosphere indicate about 30 ppm. And note this is against a log scale. But the LNMS measurements and the LGC measurements and a bunch of measurements taken in situ by Soviet probes all obtained really, really, really high water, way outside of any chemical modeling. So once again, like this is kind of a wacky result. But what we're suggesting here is this SO2 in water has nothing to do with atmospheric gas abundances, and it's everything to do with being an aerosol decomposition gas. So to summarize, instead of treating the SO2 and water, etc., as altitude profiles, we thought, well, let's treat this as an evolved gas profile, which means instead of plotting altitude versus mixing ratio, let's turn this on its head, if you will, and plot SO2 abundance versus the temperature experienced by the inlet clog. And that then gives us some version of thermal decomposition profiles. So that's this result over here, in which we've taken SO2 number of molecules, not mixing ratios, and plotted that against the LNS inlet temperature when these inlets were heated approximately 20 degrees or less above atmospheric temperatures. And on the top of this plot, we have the relative altitude of measurement. So when we did this, we realized that we changed the overall shape of the plot. And now we actually realize that we could fit these Gaussian functions. So it fit one peak and the second peak to a Gauss function, representing two different release temperatures. And from here, we're able to get an overall sum peak, which matched the data really, really nicely. So from here, we were able to get two different temperatures of maximum decomposition. And since it's a Gauss peak, we're able to get peak areas, which gave us the total number of SO2 molecules that were released from the decomposing aerosols. So to speed up a little bit here, we did the same thing for water, did not treat it as an altitude profile, but treat it as an evolved gas analysis profile. So this is the water profile. And here's a blow up of what happened, let's say, during the clog, where we see lots of different peaks, which basically suggested that water released at several different steps during the thermal decomposition. So we also did the same thing for SO3 and oxygen gas, which we're suggesting comes again from thermal decomposition of the aerosols. And we did the same thing for FeO+. There are substantial counts of the right mass for FeO+, which we're suggesting comes from ferric oxide. So combining all this information together, I can overlay these plots of SO2, water, O2, SO3, and Fe2O3. And what we see is that there are gases that were released during the clog, and this is across one temperature regime. These gases included SO2, water, and O2. But then there's a whole separate set of gases and compounds that were released at a separate temperature regime. And this included SO2, SO3, water, O2, and ferric oxide. So putting this together, we suggest that the aerosols in the clouds are actually not composed of only sulfuric acid, but have multiple components. And this included sulfuric acid, hydrated ferric sulfates, some other uncharacterized hydrates, and other species that release water. Well, there's a little solution-based water and species that are hydrated and others that release water upon thermal decomposition. So knowing these species allowed us to come up with thermal decomposition reactions, and these are shown here. And note that these chemical reactions have very specific stoichiometries. So from this information and the peak areas, as well as indicating or realizing that perhaps when ferric oxide, which is the thermal decomposition product of ferric sulfates, when that flew into the mass spec, it underwent electron ionization and most likely formed FeO+. So putting this information together, we were actually able to come up with relative numbers for weight percent of these species inside the aerosol, as well as mass loading. So in this next slide, I just sort of give you the weight percents. So this is a pie chart of what was released from the aerosols and what may be in the aerosols. So basically what we see is that yes, there's sulfuric acid, but there's also ferric sulfate, and their masses are comparable. So most people think these aerosols should be dominated by sulfuric acid. Our results say that's not the case. There's actually a considerable amount of iron in there. But we also see there's a lot of water that was released, substantial aerosol water, and that most of this water was released probably from the hydrate phase, but perhaps some of this water is also released from the thermal decomposition of inorganic, insoluble organic matter, which we're working on right now. And we say that because most of the water that we measure was released at a really, really high temperature. So considering that we saw release of gases at two different temperatures, if we actually just take the gases that released during the clog, SO2, O2, and water, we actually come up with these relative percents of sulfuric acid to water. So why that's important is that if we assign this as the volatile fraction, it turns out that these numbers then are completely consistent with what's measured by near-infrared spectroscopy and polarimetry, which indicate abundances of 75% more of sulfuric acid. So at least in this analysis, we remain consistent with what's known at Venus. So then to conclude, our reanalysis of the LMS data after 45 years of collecting dust in an archive facility yields a bunch of new information. Our CO2 profile suggests near surface haze layers. Our N2 profile reveals uniform mixing in the deep lower atmosphere, but twofold higher abundances of N2 in the clouds. Our N2 isotopic composition is actually between solar wind and earth nitrogen. And we also show that the aerosols contain abundant water, iron sulfates, and sulfuric acid. And what's really cool is by comparing all the different Venus information that we were able to collect, that we're suggesting that all Venus cloud probes actually inadvertently captured aerosols and measure their contents, and they all measure high water abundances, presumably water coming from hydrated materials. And with that, I think taking this together, this offers new considerations for cloud chemistry and cloud habitability models. And with that, I thank you for your attention.
Okay, thanks, Rakesh. Okay, we have to run on to the next talk. Scott, you're up. I guess you can share your slides.
Yeah, hopefully Zoom will let me.
Yes, it will. Of course it will. Looks good.
All right, see that? I thought dinosaurs in the snow would be appropriate for this here, Phanerozoic climate changes. So to summarize what I've been doing and what this project will consist of, this is part of our ICAR, is to do 36, or what I actually have in the end is 36 simulations of Earth's Phanerozoic that are complete with an asterisk there, that span a period of 20 million years ago to 520 million years ago, which is essentially about the beginning of the Phanerozoic. These runs are going to be extended for some modest amount of time once we have the ozone chemistry working. All of those will get interactive ozone chemistry to make the ozone layer at the appropriate time self-consistent with the rest of the climate. And then for the relatively nearer time periods, we are also going to add vegetation. And Nancy, I think, will discuss some of this. We have this done, at least in a kind of a proof of concept for 85 million years ago. And so hoping maybe, yeah, I mean, sometime this year for sure to get the paper submitted, maybe summer. I think I've been thinking this for a while though, but I think we're close to having all these components ready to go and put them together. And then it's just a matter of running them and then analyzing the output. So the choice of our time periods, we're kind of using a mix of some fairly recent references. There's this nice paper by Lee et al., which uses the CESM model to do a sort of similar task to what we're doing. And then there's a variety of Scotese references to kind of find the interesting time periods during the Phanerozoic where we have sort of maximum or minimum surface temperatures. There's maybe periods with the rapidest change in temperature over time, maximum and minimum in surface land fractions, surface albedo, or sort of other known major events. We have the 50 million years ago, which is near the PETM, thermal maximum. And then Linda was the lead to kind of help us pick the range of carbon dioxide values for each of these time periods. our goal was essentially for each time period to have a sort of low, middle, and high CO2 mixing ratio based on literature values. I'll show here in a moment. That worked for some time periods, some other time periods it didn't really work because those runs crashed for whatever reason. And then, of course, we need also then the surface boundary condition. So I took the 1 degree topography maps of Scotese and Wright, which actually not only have the land topography, but the bathymetry as well. I don't know how that works, how they do that in the past, but they did that. And then I degraded those to 4 by 5 degrees to match ROCKE-3D's native resolution. And I essentially made the ocean bathymetry a bathtub. I have continental shelves. Some of the runs had to go in and deepen the deepest part of the ocean because I kept getting the ocean freezing to the bottom, which I know many of you have experienced in your simulations as well. So most runs have a maximum ocean depth of 1,600 meters. Some I have to go like really deep. I think a few have 5,000 meter deep oceans. And then, after I got these maps, I had to do a variety of hand adjustments because there would be like random, ocean cells in the middle of the continent and, these narrow channels and things like that. So I had to do a little bit of hand adjustment there to kind of clean things up. But, this is an example here of the late Cretaceous, the 85 million year ago period. And then for the atmosphere, I followed something that Chris has done in the past, which is essentially, we're going to assume that the mass of nitrogen and argon in the atmosphere is the same as the modern mass of nitrogen and argon, but we're adjusting the O2 mixing ratio, CO2 mixing ratio, and methane. And so you kind of put those all in and you can recalculate the global mean surface pressure, molecular weight of the atmosphere, and so forth. So this is a chart, for example, of what the global mean surface pressure is over the different simulations. You can see our different time periods, the kind of darker looking points there because there's multiple simulations at those different time periods. And there actually are very slight differences between those because of the different CO2 mixing ratios. For every time period, oxygen and methane are fixed between the different simulations. Only CO2 would vary within a particular time period. So you can see that pressure basically increased more or less until about 300 million years ago, and then it started decreasing, and a lot of that is oxygen. Oxygen was much lower in the distant part of the Phanerozoic. So here, some initial results is global surface temperatures. So kind of the upshot to all of this is that we are typically colder than a lot of kind of what the literature expectations are for different Phanerozoic time periods, at least in terms of climate modeling. I know the sort of geologic proxies are kind of all over the place in some time periods, but so comparing to, again, that Lee et al. Paper using the CESM model, their values are in the dashed line. You can see that for the most part, they're kind of on the upper end or even beyond the upper end of what our ROCKE-3D simulations have. And where we do have sort of a semi-reasonable match, it usually means we're kind of at the highest CO2 mixing ratios for any particular time period. The Scotese 2015 temperature predictions are sort of similar to Lee, more or less. So also kind of on the upper end. I would expect, based on some previous work that I've done, other projects, that I think we'll probably increase temperature a bit for these on the left. If you can see my cursor, the more recent time periods once we add vegetation, and I think probably also the O3 maybe is a little bit more of a wild card in terms of whether that will increase or decrease temperature, depending how O3 varies with time. I mean, certainly time periods with higher O2 would presumably also have higher O3, and so that might help bump things up. And the later time periods with lower O2, you probably get the reverse effect. You probably have lower O3 and hence lower temperatures a little bit. So that's kind of in the later, or sorry, the farther distant past time periods. And just to kind of for reference here, you can see the different time periods, and so the solid lines are sort of the upper and lower bounds for each particular time period. So plotting those again, kind of scattered versus CO2. And this is sort of interesting is it's not as, maybe linear as I would have expected prior to starting these simulations. There's a lot of scatter, particularly sort of at, I guess what I'd call low to medium CO2 mixing ratios, sort of between, less than modern to maybe twice modern values or so. There's a good amount of scatter in there. You can see a range of like 35 degrees Celsius for similar CO2 mixing ratios. And then kind of once you get beyond about 700-800 ppm of CO2, you get a kind of a very shallow linear increase in these simulations. But again, it's not kind of as strong as I might have intuitively expected prior to starting this work. So that's sort of interesting. Again, we're kind of like, the ROCKE-3D simulations, or these ones, I should caveat, seem to be a little bit cold, just kind of generally. And that's, again, kind of something I'd found also when I'd done sort of bare ground simulations in the past. So I would expect that might change a little bit when adding vegetation. But again, these more distant time periods, we're not going to do that because we don't have any information on vegetation at those times, if there was any at all. Precipitation, I think someone was mentioning in the earlier talk before the break about, the sort of more first principles response between temperature and precipitation, and our simulations really do show a very linear response between temperature and precipitation. So I guess that validates the simple intuition and the simple model. But that's sort of what you would expect, and also really robust here across 36 different simulations. As far as precipitation, again, sort of kind of broaching the last couple of plots, is that compared to the Lee paper, again, we're typically a little bit drier because we're also a little bit cooler. But there are, again, kind of certain time periods where we have the most divergence, 170 million years ago, and then these ones where there was expected to be really rapid climate change in a variety of directions. Around 300 million years ago, we also tend to be sort of cooler, drier than what Lee showed. So that is worth some further exploration. So what is coming next? Like I said, paleovegetation. This is the chart from Nancy's paper showing these different vegetation biomes and how they're put into the Cretaceous era map. And we're using sort of the climate output from my current simulation, which of course is without the vegetation itself, to put in the appropriate vegetation based on that sort of climate at its current equilibrium. And then we'll run this forward until it sort of reaches a new equilibrium. So that'll be exciting to see. So where do we go from here? I think, yeah, I'm interested to dig in a little bit more as what is producing the scatter, particularly in these lower mixing ratios of carbon dioxide with surface temperature. Is it sort of factors of land-ocean fraction? That's kind of presumably the first step is looking at that, and then how that links to atmosphere and ocean circulation. And then why are we getting kind of the most divergence from other papers from the Lee paper at certain time periods? I had to really, for 170 million years ago in particular, I really had to deepen that ocean to avoid freezing. But it's because it kept getting cold even with other, ocean depths, obviously. So, I think the cold climate is something that Rocky seems pretty enthusiastic about at that time period, but does the deep ocean itself have any impact? I don't know. And then, what other variables are worth looking at here in the sort of the overview scale that we're looking at for an entire terrestrial time period. And that's it.
Okay, great. Thank you, Scott. We've got time for question or two. Chris, go ahead.
Two quick ones, Scott. I probably the community standard is going to be the Judd reconstruction. I'm guessing we should probably compare to that by the time.
Okay.
published. As far as the CO2 temperature scatter, so I mean, there's also like solar radiation evolving over the Phanerozoic. So probably
Sure.
a better plot would be just like the difference since each time slice has different CO2 values, we can do a climate sensitivity, like how has climate sensitivity evolved, but just like temperature
Yep.
against CO2, because you got all these other forcings evolving over that whole interval, so it's kind of confounding them.
Yeah, I think I did that climate sensitivity plot like 6 or 8 months ago. Yeah, I can easily redo that. Yeah.
Okay.
All right.
I have
Thanks,
more
everyone.
questions, but I think I should save them until next time.
All right.
Can you stop sharing? Okay, great. Thank you, Scott. That was great. Linda, you're up now. And we have a pointer over here. I can give you my seat if you want. Just to get Zoom to share. Good. Can we get rid of this? You want to sit here? You can sit here.
Okay, so this was a joint effort. Mark and I have been doing some of the climate analysis. Of course, Kostas took care of doing the aerosol runs for us, and Jeff Jonas helped out with the initial setup. So some of you may remember a few years ago in Journal Club, we read this particular paper by Liu et al. Where they discussed their finding of a really strong influence of dust on the Precambrian climate. They point out that dust is not commonly included in paleoclimate runs. And in the simulation that they ran, which was for the late Neoproterozoic, just before the glaciations begin, so specifically a non-glacial period, they found that adding dust would change the global temperature by, I should say, at least 10 degrees C, because the 10 degrees is the difference between no dust and the lowest amount of dust that they added. For the higher amounts of dust that they added, the cooling ended up somewhere in the order of 20 degrees C, which is a lot. And we thought this sounded interesting, shall we say. So we decided to test this out with ROCKE-3D. So this was version 2, but at the higher resolution, so that Kostas could work his magic with the aerosols. So it's 2 by 2.5 atmosphere, 1 by 1.25 ocean. And we use the GISS radiation for this, not Socrates, just because it would be faster with the interactive dust. So the reconstruction that we use, that you can see here on the slide, is from Scotese and Wright. And so this is a reconstruction from 450 million years ago in the Ordovician. Why did we choose this particular time period? Well, this happens pretty much before the first land plants with roots become established. And so this was an example of the latest possible moment in Earth history where we could look at something that was probably not extensively vegetated, if at all. There may have been some things like bryophytes hanging around, but they do not have root systems, and so we don't expect them to impact the environment quite so much. We chose a CO2 value of 8 times pre-industrial, and this is sort of confirmed through various geochemical models and some paleoproxies that we have for this time period. We left methane and N2O at pre-industrial levels. We had a reasonably deep dynamic ocean. And we ended up running a total of 13 different experiments. I know the type here is small, but I'll just summarize this briefly. As our control run, we had a no aerosols simulation. We did one using pre-industrial aerosols as a NINT run, just for comparison. And then we had a number of prognostic dust runs. So one of them, which is DU-KT, was simply the dust that became entrained as a result of using the Ordovician geography to drive dust floating in the atmosphere. And then we use that as a baseline for varying a couple of other dust levels. So for dust level of 1/10 of that, as well as 10 times that. We had a simulation where we did not restrict dust source areas to areas in valleys or around river basins, but instead we made every potential land surface a dust source. And then we also did some experiments looking at sea salt as an aerosol, either by itself or in combination with dust. And then we had a couple of interactive chemistry runs at the end, and one run where we eliminated the long wave component of the dust effect. I have more maps than anything else, and I didn't want to bury people. So I'm going to show just 4, which are exemplars of the findings that we have. So on the upper left, we have, these are all anomaly maps. On the upper left is the anomaly of the DU run, minus the no aerosols. On the upper right, we have DU10, so 10 times the amount of dust, minus our control. On the bottom left is our sea salt only simulation. And on the bottom right is sea salt combined with the 10 times dust. And I think it's really apparent from this particular set of maps that sea salt has a sort of a minimal contribution. And a lot of these temperature changes are pretty small. So, oops. So this is not going to show. Yeah, okay. So for the DU anomaly, the mean change is just minus 2.3 degrees Celsius. For sea salt alone, it's actually a little bit warmer, 1.1. For the 10 times, for the sea salt and dust, this is minus 1.4. And for this supercharged sea salt and 10 times dust, this is minus 8. For the temperature. When we look at the change in planetary albedo for these same 4 runs, it's pretty clear that the mineral dust is taking control of our simulations, and it is strongly associated with the land surface in the southern hemisphere, or supercontinent of Gondwana at this time. And then, oops, something. Oh, this was incident solar radiation. Incident solar radiation and planetary albedo. So the mineral dust is driving most of the difference that we can see in these runs. And so this is unfortunate. This is a large table of values. The column that's outlined in red is our SSDU10, so that's the combination of sea salt and 10 times dust. That has the greatest difference ultimately compared to our control run, which is the column outlined in blue. And the temperature difference, and I misspoke before because I was looking at the wrong slide, the temperature difference for the mean global temperatures is about 2.5 degrees C. And that's the strongest impact that we have in these runs. There's actually not a large amount of variability in a lot of these particular diagnostics. So for the level of effort, I will just say for the level of effort that Kostas had to put in to do these runs with dust, we probably don't need to worry about it quite so much, at least for Earth. So why the big difference? Liu et al. Gets 10 degrees C at a minimum, and we get about 2.5 degrees at a maximum. Well, The first thing that comes to mind is model sensitivity for me. This is CESM 1.2.2, so it is not the same version that was highlighted a couple of years back as having a very high sensitivity compared to other CMIP6 models. But yet this result from their this table from their supplement highlights what looks to me like a pretty significant sensitivity effect. So this is their control run at the top with no aerosols. That has a temperature of 14.5 degrees C. And then these are the increasing levels of dust that they are loading to the atmosphere. And the DV is a set of simulations that they did where after these runs achieved equilibrium, they started a new run by and added vegetation to see what the effect of adding vegetation back into this would be. Now, they were looking at the Precambrian. There was no vegetation in the Precambrian, so they just used modern. But one of the things that you can see...
You said there's no vegetation in the Precambrian, they use modern vegetation.
Yes. But there are a number of
strange things in this paper.
Strange things in this paper, and I won't even touch on what Ron Miller has to say.
Too bad Ron's not here.
Yeah.
So do they have dynamic dust or just prescribed?
So this is prescribed dust. So they're looking at it as related to a surface erodibility factor, essentially. And so this ends up being minimal erodibility. This is their maximum erodibility here. And the temperature differences at the, even at the low end of dust loading seem fairly large to me. So the global average temperature with the minimal dust loading is 3.3 degrees C. Add vegetation back and it's 9.8. That's a lot for adding vegetation back. I have done simulations where I looked at modern Earth without vegetation and with vegetation, and in the GISS model, there's like 2 or 3 degrees difference, global average. But this is a lot, And then here for the next level of loading, we go from 0 degrees C to 7.5, and so you can see that every step that they take provokes a fairly large response. And it's not clear to me why that's happening, and they don't.
It's like surface albedo is changing huge amounts, 6%.
Yeah.
That's probably the big factor in the surface temperature, because so it looks like the vegetation is changing the surface albedo by 6%. Does that make sense?
Yeah. Well, in their version of
and that's global, right? So ocean doesn't change; it's just over land. Land is what, a third of the surface area?
So land is about 20%, but their land also is more. I can't really say it's equatorial, but there is more in equatorial regions. So over the area that would normally get the most insolation compared to ours, which is definitely a southern hemisphere oriented boundary condition. So geography may be playing a role in this.
Do they try in the paper to explain the big variability in their system?
They just say they haven't. and they report it on a seasonal basis as well. For some vacation. Yeah. And the last reason is that they make some assumptions about dust and dust erodibility, which even to my reading and not being an aerosol specialist seemed a little bit unusual. First of all, they are pulling their erodibility factor from a model that looks at modern soil distributions, and so the properties of the materials are probably not even the same to begin with. So I would question using this particular model for something that old. They do specify a uniform source area. Because we don't have topography really available for the Neo-Phanerozoic, I understand why they made that decision. But they say it doesn't really matter much looking at the modern, and I would argue differently. So that may be a factor, but we don't have a good control for it. And then this last point here, you know, the volume of potential sediment source or silt that is windblown is actually far greater after vascular plants appear. You would think that a desert-like environment would have lots of windblown dust available, and they argue that that is the case. But they also get confused here because they talk about looking at Earth's climate in other points in the past. For example, the last glacial maximum. They say, look, you know, it was cold and it was dusty, but the dust didn't make the climate cold. The dust is an outcome of the climate being cold and glaciers doing their thing, grinding up the landscape. So they have some inappropriate ideas about where the silt might be coming from. And I'll also note, I put this in from a paper from 2018, that shows what the expected impact on the availability of silt and clay to make mudstone is over time. And here we are at about 450 in the time period that we're simulating. You'll see that there's much more of that type of sediment available later in Earth history and not before.
Linda?
Yes.
The vegetation can have two opposing effects on the dust. One is cover, of course, that will reduce the dust, but the other is roughness length, which the vegetation increases, which increases the coupling with the atmosphere, which then can increase the exchange. So those are, so it depends on what's the balance.
Yeah, no, for this Fisher paper, it was strictly a matter of trying to understand the development of significant quantities of silt and clay in the sedimentary record for Earth history. And they point out that it doesn't come up until you have vascular plants, which not only break things apart physically, but also introduce some chemical erosion. Okay.
Well, right, they also increase the roughness of the surface.
She heard.
Yes, I know.
Yeah.
Nancy, you're up next. Thank you, Linda. Great work. Please
talk
about this in one of the bi-weekly meetings.
Yes.
All right.
This is so good stuff. Oh man. Okay. Nancy,
okay.
Go for it.
All right. Let's see if.
15
all right.
minutes.
Let's see if this will work. If I share my screen.
No work. Great.
Okay. All right. Are you by sharing my screen? Share entire screen.
Slowly but surely. If you have started screen sharing, come on. What are you, super high resolution here? Are you still there, Nancy? She froze.
No, she froze.
Oh no. We lost her. Okay. Oh, she's gone. Okay.
Maybe you're gone.
Maybe I'm gone. Can anybody hear us?
Yeah. I mean, maybe the connection is too slow. So
her image disappeared though.
Maybe resume.
Yeah, she started to share and her image disappeared. Basically, that means that there is somewhere at the bottom.
Clear. Yeah. Can anybody else hear us online?
I can hear you in Seattle.
Awesome, great. So it's not us.
Or maybe it's Nancy's.
She disappeared completely. Oh, there she. No, she's down there now. Okay, let's see.
I'm not sure what happened. Sometimes the NASA Wi-Fi here flakes out. Can you?
Try again.
I do not see anything right now. Okay.
We're here.
Okay. Can you? I can't.
We see you. We don't see your screen.
You can see me. You can. I think I'm gonna have to exit and come back. There's something wrong with the connection. Sorry.
Okay,
oh, now it's coming. Now it's coming back. It seems to be very slow. Okay. All right.
Maybe turn your video off, Nancy. See if that helps.
Okay. Well, all right. Can you share my screen without the show?
If it doesn't work, we'll switch to the next one and then let you try it.
Okay. All right.
Let's see what happens. Give it a try.
All right. Can you see
There
this?
we go.
Oops, let me.
Yes, that's it. Go for it.
Okay, let me. All right. Go back to. All right. Can you see that? Full screen?
Go.
Okay. All right. Okay.
Yes.
Okay. Surface phototrophy and feedbacks to climate. And there's going to be 2 projects presented here. And this is supported also by SEEK grant. That's in the second year. We're going to cover three different time periods. First project covers Cretaceous through modern, and the second talk will cover the Neoproterozoic. Okay, so there are different things that happen with evolution of plants. Okay, first one is just on the Köppen-Geiger tool for generating vegetation boundary conditions for alternate climates. Some of you have already seen some of this presented at a ROCKE-3D meeting. This was done with my career, James Liu, who James, you're on. You can chime in. James was highly instrumental in a lot of the methodology in the coming up with our lookup table, and then Linda and Scott have provided the scenarios and the climate for us. This tool was created because, according to Sohl, one of the most time-consuming and often daunting tasks for paleoclimate is the production of surface boundary conditions for past time periods. So this is a constant challenge. The biome family of models by Haxeltine and Prentice have been largely used for the PMIP model intercomparison products for paleoclimate to prescribe vegetation, and they do various things at daily and monthly time steps. So this is another take on that that will be a little less cumbersome than running the model. So DGVMs do these various levels of dynamics, biophysics at the physical time set, biogeochemistry, daily seasonal, biogeography. And the thing is, we don't need to do the latter two, biogeochemistry and biogeography, for these paleoclimate simulations. We're not doing full-blown carbon cycles, but you do need the biophysics to affect the climate. So the biophysics involves having the CO2 exchange coupled to H2O exchange, and the roughness lengths and the albedos of the vegetation. So how do we get the vegetation boundary conditions? So what we did was there's something called the Köppen-Geiger climate classification system, where climate based on temperature and precip alone is classified into different classes which match with vegetation biomes. And so they are here. You can see them listed here, and it's about some categories have 34, and there have been updates to this scheme. This is the latest, and there's some improvements on it. So this is not necessarily the best one, but it's pretty good, and it's often relied on by future climate change people and people trying to project impacts of climate change on things like crops. So we take this, and for each biome, there's a mix of vegetation types. And those vegetation types have their particular physical characteristics and seasonality. So if you take this map for the modern observed climate and use it as a mask on modern observed satellite vegetation structure, and these are the vegetation inputs to Model E. These are what's default for the Earth system model at GISS. And then we can come up with a lookup table of what those properties are. James did a lot of gymnastics with statistics and came up with various histograms and finding out the peaks of those histograms for the distribution of heights in a biome, for the distribution of LAI, the distribution of cover fractions of different plant functional types. And we came up with a seasonality for Northern Hemisphere and Southern Hemisphere, also for the leaf area index. This is just showing one biome type, the broadleaf evergreen rainforest. And then it eventually got a lookup table. And so you can see it's pretty reasonable. You're not familiar with these types, but for example, AF is basically rainforest. It is pretty much mostly evergreen broadleaf tree. And then you got some arid types that have some mix of grasses and drought deciduous trees, etc. So it all came out in the wash pretty well. And so we use that as a lookup table. And now that's modern vegetation. So not all modern types existed way back when. So we came up with a widget. Actually, James came up with this widget to ramp in the prevalence of different types of modern vegetation as they were introduced and as they emerged on the land. So these are the time periods, and this is when they emerge and how they kind of ramp up to what year or what million years ago they ramp up to their modern level of prevalence. So you got C4 grasses or kind of later, and deciduousness, was a certain point too. So if we use that, that's a second step to replace the modern lookup table results. And now we wanted to see if, well, if you make these biome types and they're kind of homogeneous around for their particular type in terms of vegetation structure, how does that affect simulated modern climate? So you reproduced the vegetation boundary conditions from the lookup table, and then simulated modern climate compared to the original Model E input files. And we see that, well, there's not a big significant differences for surface air temperature and precip. So I guess that's so it was efficacious to have this simplified specification of biome types. We also looked at things like GPP and NPP, those gross primary productivity and carbon stocks, and those were also within uncertainties. So that's pretty good validation that this little lookup table is okay. And then we applied it to the paleo climate. And Scott already presented to you these plots, and I'll just go in a little more detail. It's compared to a fossil reconstruction. What we have here is the Koppenbayer biome classes in plot A, and then the modern types that would result from the lookup table. And then you do a next step to replace the modern types with the paleo types. And this is what you get on plot C. And also there's some of the distributions of the canopy heights and the maximum leaf area index for that time. If you compare our paleo vegetation, which is based on a bare soil climatology before we had vegetation in the ROCKE-3D, we were too cold in the higher latitudes. The trends are generally, pretty consistent with what you see in soured and latitudinally. So you've got your shrublands down around the equator. You've got some evergreen forest and woodland in the middle and the equator, and then grading into evergreen forest. And high latitudes but it's not cold, it's too cold, so we're getting more evergreen needle trees and not getting the broadleaf deciduous trees. So we'll see if the GCM has biases at that high latitudes that will be rectified or not with vegetation being put in asynchronously. So we have this nice handy dandy lookup table tool, and I'm submitting it to either Journal of Biogeography, but it's too long, so maybe I'll submit it to Paleoclimate Journal. So Scott and Andre are using it for the ROCKE-3D runs. Sonny and Kostas are using it for their runs, and so we'll see how the biome people like what we did in the reviews. So there are other things that could be improved. Obviously, there's lots of debates on paleo vegetation, so those algorithms can be improved. And I'll leave it to the community to add their own little script widgets to do those updates. LAI seasonality could be updated to look at amplitude and timing instead of just the mean LAI for a decade. Okay, so next, by the way, I just did a quick plot during today showing of the Phanerozoic vegetation, but it would be good if, Andrea, if you could come up with the continental boundaries for these time periods, and I can put these on these plots. And we'll, I guess, Linda, if you can take a look and tell us if that looks kosher with what's known about these time periods, that'd be great. Okay, all right. Okay, next one is looking at further back primitive stuff, snow microalgae effects on surface albedo. And this work was done by this work was done by Vidya Fenkatsen, who's a student of OMA Shields, and she's a real go-getter. She installed all the packages and everything and got ROCKE-3D running on the system over there. So the idea is that during the Neoproterozoic, there were algae that emerged, and there certainly must have been snow algae that would have been darkening the snow and altering the climate for that period. So she decided to put snow algae albedo into ROCKE-3D and see how they affected the climate of a slush ball Earth. And so for this reflectance of the albedo, we got one of our co-authors, Lydia Coelho Fonseca, and she's been measuring lots of bugs out there, and she has measurements of this chlorophyta snow algae on both wet state and dry states. And so what we did is we took a mixed state, 50-50 wet and dry snow algae, and this bottom plot is from a simulation by the SNCR snow radiative transfer model, where they were looking at the effect of snow algae on the snow albedo. And you can see the effect pretty much cuts out at around the end of the 700 nanometers, where chlorophyll kind of stops absorbing. So that was cool. So we applied Lygia's albedos in the visible in ROCKE-3D. And this is our setup. If you want to go, that's in the albedo.f, a bunch of if defs. And it just prescribed 50-50% cover snow versus cover algae. And the period time was with Sturtian was about 40 ppm CO2, and the solar constant a little bit lower. Everything else is Earth, and then it was Sturtian continents that Linda provided. And we had initial conditions from a Planet 1.0 run, so we ran Planet 1.0 so that they would not have to spin up the GCM ocean. Okay, so this is just how it. Is
this merged into the model?
Sorry?
Is this merged into the model?
This is what. No, it is not. So if you like her to or me to do that, we could, but it was Planet 1.0. It's just if deft, and you can set snow algae as an option in the run deck. But it's Planet 1.0, not Planet 2.0. Okay. All right. And all right, so this is how the runs spin up, and for the northern, southern hemispheres and global. And the top are what happened with the snow algae, and the bottom is just without the snow algae. So you can see it got warm and equilibrated within 30 years. So that's not, so she didn't have to take too long. And here are our results. Ground temperature, ground albedo, snow ice fraction went down, planetary albedo went down. And she also did a Donahoe and Battisti analysis to see how much of the surface versus atmosphere contributed to the planetary albedo. And the clouds went up with the snow algae. Anyway, basically this drastic precipitation of snow algae raised the global mean temperatures by more than 12 degrees. So maybe that could help warm the planet from snowball states. Or maybe give better credence to slush ball states. And what else? And the warmer planet also caused overall decrease in wind speeds. And she has a few other results I won't show. But anyway, we got snow algae on snow. It warms the planet. And you could have maybe more realistic implementation of the algae, where they would be dynamic with the snow age and the thaw state of the snow. But she is now, we're meeting actually with Vincent Kaufman tomorrow, so because she was really keen to do a PSG observation simulation for the detectability of the snow algae. And that is that. Thank you.
Great. Thank you, Nancy.
Okay. All right. Stop sharing.
We're going to have to go on to our next talk. Vasuda, are you there? Do you want to share?
Yes.
Nancy, could you stop sharing?
Oh, yes.
Okay, Vasuda, you want to share and show your presentation?
Yes.
Excellent.
Give me a second.
You can always ask questions in the chat if you didn't get to during the talk. Okay, great. We see it. Looks good. Go ahead.
Sounds good. So hello, my name is Vasuda and I'm from University at Albany. I'm Dr. Kevin Knuth's PhD student and I'm graduating soon. So today I'll be presenting a Bayesian machine learning framework that connects climate simulations to exoplanets' atmospheric absorption spectra. And basically this model will be acting as a forward model so that we can infer planetary parameters given an atmospheric absorption spectra. So this model will be trained on both actual data and synthetic data from ROCKE-3D GCM model. And the resulting study, which will act as a forward model, will basically help us infer the planetary parameters from the spectra. So what we are doing is we're modeling atmospheric absorption spectra as a set of 20 spectral bins. And aim is then to predict these 20 bin heights based on 30 planetary parameters. So basically the height of each bin will be a function of 30 planetary parameters. And by considering different models, for example, uniform binning, optimal binning, Bayesian block, we are aiming for efficiency. So I'll be discussing more about this binning techniques and which one came better with the results in the later slides. So as Professor mentioned earlier about it, that we synthesize some data using the 6 functions. So basically, this is a synthetic spectra of a proof of concept. So we had defined these functions so we know what the functions are. So we are going to see if we can recover them or not. So this shows how the planetary parameter X changes and how different bins will vary as a function of X. And the data we are using to train are basically the 6 illustrated spectra at these values of X. So for the concept one, we used PCHIP. And in the conclusion, this method worked well with one planetary parameter, and PCHIP spline curve model the variability of the bin heights well. And the application of Bayesian adaptive exploration was extremely effective in determining which regions of the planetary parameter space need to be better sampled. And it is clear that the spline models will not scale well as planetary dimensionality is increased, like we are looking into 30 dimension. So it might not be a better method in that regards. Whereas Gaussian process, it appears to be more promising model for the spectral bin heights, and it motivates us to use Gaussian process regression, which is our concept 2. And this was a concept 1 paper which got published in MDP in Magazine Journal, which Professor mentioned earlier. So now the concept 2 of using Gaussian process regression. So Gaussian process regression, it's basically a Bayesian non-parametric model. And instead of defining the spline knots explicitly, Gaussian process treats the function as a distribution over possible function. And this allows smooth interpolation and uncertainty quantification. So in order to keep it consistent to the first method and see how it is behaving, how Gaussian process regression is better than spline curve, we try to keep it similar to that. Like we're only considering one planetary parameters. Prior distributions are defined by k prior data points, and we're only considering 6 spectral bins. And similar to spline modeling, we use Knuth sampling to estimate the posterior and height of the Gaussian process priors for each spectra. And 6 points are used per bin, with the endpoints fixed at 0 and 1. And the other 4 is allowed to vary. And we also at least keeping them at least 0.1 distance apart and using a sigma value of 0.1. So on this slide, we compare different Gaussian process kernels. Gaussian process kernels, they're basically covariance function, and they're also key components for Gaussian process modeling in machine learning. So they define how the output at different inputs are correlated. So we tried different kernels, like case one using like squared exponential, rational quadratic, just squared exponential, just rational quadratic, Maton, and the combination of these. So we decided like go on with the case 5 and case 6. We also collected the evidences with noise and without noise to see and compare which model is working well. So now in the next slides, over here, this figure shows how the Gaussian process model smooths the spectral curves and predicts bin height. It closely matches the true synthetic spectra. It's a scalable approach for future multidimensional modeling. So illustration case 5, it shows it's using the squared exponential with Maton v is equal to 3/2 kernel. And it's showing that the spectral before running the Gaussian process regression and after running the Gaussian process regression respectively, and so on for the case 6. But in case 6, we're using rational quadratic with Maton of v 3/2. So our model is like basically will be scaling to in order to scale to the full dimension, we'll be building the training data set, integrating nested sampling, and constructing the retrieval engine. So it will be scale, build, train, construct, and then apply. So for synthesizing the data, we are using ROCKE-3D. So ROCKE-3D is basically a general circulation model. And in ROCKE-3D, we are varying the parameters like stellar flux, atmospheric composition, surface type, rotation rate. And this allows us to explore a large possible range of Earth-like climate systems, climate states. And it extends the Earth's climate modeling heritage to simulate a wide variety of terrestrial planets. And whatever we are getting from the ROCKE-3D, we are putting into the planetary spectrum generator. And planetary spectrum generator, it converts model output to the synthetic spectra. And over here is basically the whole synthetic spectra we have generated from warm Earth-like planets, where P211 is present-day Earth insolation, P212 is present-day Earth insolation with 1.1, present-day Earth insolation with 1.2, and for X001 is present-day Earth sidal rotation rate, and X002 is 2 times present-day Earth sidal rotation rate, and so on. So these are the spectra where our model will be trained on. so this is the whole pipeline, like ROCKE-3D to PSD to synthetic spectra. From ROCKE-3D, we are getting the netcdf files, which we are putting into our planetary spectrum generator. And then we are getting the GCM compatible files in the form of AHA, AIK, AI grids. And then we are uploading these GCM file and choosing the geometry like transit, direct imaging. And then we are running line by line correlated K on multiple scattering calculations. And then we are synthesizing the spectra. So this is again just our synthetic spectra. So now earlier I was talking about the binning technique. So we tried like 4 different binning, we tried 3 different binning techniques, and also we tried to find the Bayesian evidence for what if we are not binning and we're just feeding in the information right into the model. And over here, we can see that this plot shows that the Bayesian evidence or log marginal likelihood for the same Gaussian process under different pre-processing choices. And Bayesian evidence, it measures how well a model explains the data while automatically penalizing unnecessary complexity. So higher value basically indicates a better balance between fit and simplicity. Here we see that the adaptive binning, like basically our Bayesian block binning technique, it leads to the higher evidence and indicating the most informative Gaussian process model, whereas like raw Gaussian process, it's like way more below minus 1000 and it's like not suitable. Whereas like Knuth binning technique is also working fine. So we used a Bayesian block and we tried to model that, our algorithm based on that, but we also like try to predict across binning different binning methods. So this plot shows how the same Gaussian process model behaves when trained on spectral binning using different methods. So the gray points represent the original high resolution transmission spectra. The blue curve over here shows uniform binning, which produces a smooth fit, but it surpasses narrow absorption features. The orange curve over here, it uses optimal binning by Professor Knuth, which improves data efficiency, but still like averages over localized spectral structures. And over here, the green curve, it uses Bayesian block, which adaptively places bins where the spectra changes the most. And it's allowing the Gaussian process to recover physically meaningful absorption feature. So the key point is that the Gaussian process model is identical in all cases, and only the binning methods are changed. And right now, over here, looking at it, the Bayesian block binning, it significantly improves the spectral feature recovery. So that's what the base of our project is. So right now, like in this Lee-1 region out validation of the Gaussian process model, what I'm doing is I'm using a Bayesian block. Bayesian block, it adaptively bins the algorithm spectra and sees like calculates the number of bins per spectra. So what I'm doing over here is I'm removing an entire contiguous wavelength region, which is in this red thing. And then the Gaussian process, like a Gaussian process model is basically trained on rest of the spectra. It has never seen this region before. And then we are asking it if we can reconstruct this region or not. So this test is basically of two generalization and not interpolation. And after running the model, we saw that like this blue line over here, which is basically our Gaussian process prediction, and these black points are which are our withheld region. It was able to recover them even though when training the model, it has never seen this region before. And this is happening with largely contained within the 95% confidence rate interval. So based on all these results, now we are like our next plan is to increase the dimensionality of the model. Right now, we are just considering a rotation rate and insolation as a planetary parameter. Now the idea is to add more parameters and increase more dimensionality and see and calculate the Bayesian evidence and see which model is behaving well. So the Bayesian machine learning framework modeling atmospheric spectra directly from the planetary parameters. And adaptive sampling, it validates with PCHIP, and its scalable inference enables by Gaussian processes. It's an uncertainty-aware surrogate linking ROCKE-3D to PSD to the synthetic atmospheric absorption spectra, and it's extensible to the multidimensional habitability inference. Thank you. Any questions for me?
Give us an spec. Yeah, sure. Go ahead, Robert.
Hey, thanks. That's a nice talk. I'm curious, is there any a priori reason to know that every one of your 30 planetary parameters ought to map into some aspect of that observable spectrum? You know, in other
I'm
words,
sorry.
You're saying that are all 30 parameters actually going to be useful in producing the spectra in some kind of unique way? We don't know the answer to that. Probably not. There'll be some dimensionality reduction for sure.
yeah.
100%. Yeah,
Thank you, Mike.
no worries. Binning is important.
And
So we're using the best binning method in the universe. Probably haven't even heard of it.
Universe.
In our universe, yes. Bayesian block. So this is developed by Jeff Scargill. He's one of the world's time series experts, and he's been using this for years. We've even used it in cosmology. It's used in Kepler spacecraft data. It's used in Fermi. It's an extremely powerful algorithm. And as you can see here, it's got the best Bayesian evidence by far, as one would expect.
almost zero.
Okay,
Yes.
we'll take
Thank
another
you.
break. 15 minutes. Thank you, Vasuda. That was great. And we'll start up again in, like I said, in 15 minutes. So get some coffee if you need that, or whatever you need. Okay, we're going to start up again here, and our next speaker is Chris, and I'm going to share some screen somewhere with him. Why doesn't it show up here? It's in my list. Let's try sharing this, and then I'll move it over. Why does it want to do that? Let me just try this, Chris. There we go. All right. I think the clicker will work, Chris. Go for it.
All right. Hi, everyone. So this is one of those kind of like speculative talks that I want people to tear down, and I think Rory's online especially. I've been thinking about tidal heating and planets, and I'm still learning about it. So I just kind of piece this together. So I wanted to convince myself that you could have. I've always just kind of thought if you're kind of near the outer edge of the habitable zone, you know, you have an icy planet, like you're just not going to get a lot of tidal heating at those distances. But I went to the NASA Exoplanet Archive, just filtered by planets that have like less than 2 installation, Earth mass C planets, you know, less than 3 or something, and then have a reported eccentricity greater than 0, so you can get some tidal heating. You can also do it if you have some obliquity, just creating non-uniformities in the gravitational tug of the planet. And then there's error bars on here from reported eccentricity values, and just calculating the tidal heating that could be experienced using kind of standard equations based on the orbit, and the big thing is the internal properties of the planets. And I have this is a log scale, so the top 10 to the 1 at the top is like, you know, will you get like less than 1.51 installation and have like 10 watts per square meter of tidal heating, and it's a stretch, but like perhaps you can with the errors in if you can generate like a 20 obliquity planet or some enough eccentricity, and this is kind of with a reasonable K2 over Q, which has to do with the internal properties of the planet. That's kind of what, you know, that could be 2 orders of magnitude uncertainty right there. This is like a reasonable value. Everything else is just a property of the orbit, the G, and the mass of the planet, the radius, the semi-major axis. These.
Sorry, to get these high values, what was K2 over Q?
I think it's like a Q100, and then 0.3 or something. So I convinced myself, at least, like, and then I convinced myself, okay, if you stretch, if you can create in like even around a low mass star, you could somehow generate a, you know, 10 obliquity, 20 obliquity, or some enough eccentricity, you actually can get climatically significant tidal heating, order 10 watts per square meter, 50 watts. Like, I don't know what these planets will look like, if they're just magma oceans, if they're chaotic and turmoil, but I've convinced myself you can get like sub 1x Earth installation and still have appreciable tidal heating, hopefully. You know, I don't know if that's just bonkers. I've also, I was interested in, can these planets, so I'm looking at, I wanted to think about the TRAPPIST system as a case study. And so over Christmas break, I was learning this rebound package, which tracks, it's just tracks particles under the influence of gravity. So you could put planets in there, you could put moons in there, you could put asteroids, you could put Tesla cars in there and just track orbits and things like that. And so I reproduced the Lascar solution for the next million years of Earth's eccentricity. And then I did some kind of fun, like if I took away Jupiter or if I made Jupiter more massive, what would the eccentricity spectrum look like? And it just that was me being playful. But then I looked at TRAPPIST-1e, which the community is very interested in, and the reported eccentricity of TRAPPIST-1e is something like 0.005, very small in a compact system. This showed me I can get up to like 0.02. And then I did some hypotheticals where I like doubled planet D's mass, and you can get a little bit more 0.03-ish. And then I used Rory's package VPlanet, because I don't know with VPlanet. I think you could do a one-body perturber where you can, I'm not sure if you could do more than that. Rory can correct me later, but I just put planet D and planet E in next to each other, and I said, okay, go ahead and, what is planet E's obliquity evolution and so forth. And you get locked into this like 2-degree obliquity state, and you get no tidal heating basically on planet E. I asked a hypothetical of what if planet D is like 40% Earth's mass. If you made planet D Earth mass, all of a sudden VPlanet wants to give TRAPPIST-1e a 35-degree obliquity. So I was like, okay, that's cool. Maybe you can have a TRAPPIST-like system. Maybe it's just like coincidence that planet E is, in a very low obliquity state. I've always just thought it's a compact system. You just, everything circularizes, everything goes to zero obliquity. But I don't think that's true. So I was like, okay, there's enough motivation for me to climate simulations of like, what if you could generate 10 watts per square meter, and maybe there's some way over geologic time you can pump up the obliquity enough to do something like this. And so I did this with the TRAPPIST. It doesn't make, this is just with the Q-flux ocean. This is a standard TRAPPIST run with TRAPPIST gravity, TRAPPIST radius. It's like 900 watts per square meter installation, something like that. I gave it 10 watts per square meter. It opens up the ocean a little bit. So there's a little bit of a difference just for this particular planet. And then I've been working, I've showed this once before, but I've done a larger parameter space where I just put, I put planets around these low mass stars. I play with the orbital distance. I keep the rotation period consistent with Kepler's law, assuming it's synchronous. I have a 10-year standard aquaplanet with an Earth-ish atmosphere, and I've been doing these double ridge worlds just because they kind of give a little bit. I've done the aquaplanets. This gives a little bit cleaner results, but and then I've played with different tidal heating distributions. So Rito a few years ago implemented, call it a geothermal heat flux, a tidal heat flux. I'm using them synonymously, where it just enters a heat flux into the bottom layer of the ocean, or if there is land, it would be at the land surface. And then I played with different heating distributions of that geothermal heating, where I make it uniform. So these three plots are the same global mean tidal heating, but one is concentrated at the substellar point, so it kind of inflates the substellar heating. One is on the night side, and one's uniform. And I kind of increase. There's no reason this needs to be the case. In some cases, a closer in planet will just become synchronous easier, and it might not have any tidal heating. But in this case, I just keep tidal heating. It increases monotonically as you get closer to the star. So this is now playing around with the distribution of the tidal heating. This is a case of around a 2600 Kelvin star with a 60% stellar flux, where I put the heating at the substellar point, and then at the antistellar point, you start to open up. So the planets are otherwise identical, except for just where the heating is distributed, and you open up liquid water on the night side when you don't. in the other example. There's another case study where the heating is, these both have 70% flux around a low mass star. The left is uniform tidal heating. The right is substellar concentrated tidal heating. These are different planets. You have a completely ocean covered world, and then you have ice on the next side in the right side. And then just another example, this one around a 3000 Kelvin star, 55% stellar flux, Earth stellar flux, and one where you have substellar focused heating, and the other one is anti-stellar focused heating, and that it's not enough to thaw out the night side. In this case, in this example, removing that tidal heating on the day side freezes that side over. So basically the point being that where the tidal heating is concentrated, it could matter for these snowball states and what they look like, even for the same otherwise boundary conditions. And so that's what I've been playing with, is just trying to convince myself that tidal heating can matter on snowball-ish worlds or water worlds with ice. I still don't know if this is one of those things that just might be fatally flawed. Everyone might just say you're never going to get more than 0.001 watt per square meter on these worlds. But I've convinced myself that you can, and then that can matter for near the outer edge of the habitable zone. So yeah, I'm just playing with that, and kind of fun results when you add tidal heating to a snowball story. That's all.
Okay.
Next.
I think a lot of it depends on this K2 versus Q thing in the rheology, right? Because there's a paper by Makarov, I don't know if you've seen that, where he has highly dissipated, and he says the geothermal heat flux is huge, like orders of magnitude higher than Io.
Yeah.
So it totally depends on the property of the world.
Yeah, and
which are completely unconstrained.
Like 2 orders of magnitude.
So it doesn't. I think it's totally possible. Go ahead, Robert. Sorry.
I was just going to ask you get the tidal heating in these like bonkers orbits, right? And just
they're not bonkers orbits.
It's not even far fetched. It's just take a planet around a low mass star, make it perfectly circular and zero obliquity. You're not going to have asymmetries in the orbit that create tidal heating. All of a sudden, you give it 0.001 eccentricity or 5 obliquity or something. And
we know the TRAPPIST planets have eccentricity, so there's definitely tidal heating going on.
And now the gravitational tug is
right. Maybe they're not bonkers. Maybe they're totally within the bounds. The question though is like, does the insulation to the simulation match the orbit that you're imagining?
Yeah. You said that.
Okay. Yeah, I missed it.
But I wish you would take my TRAPPIST-1 simulations and put your stuff in them with the proper ocean instead of this bullshit slab ocean you're using. Go ahead. I think Jan was first. Go ahead.
One of the first figures you showed that maximum eccentricity is 0.5 that you assume, or Mars, for instance, has more than 0.9.
So I'm thinking for around low mass stars, for planets that are closer in, they tend to evolve in more circular, the solar system is, you can have whatever eccentricity, but it's way too far to have tidal heating. It goes like distance to the fifth power or whatever it is. But so yeah, in the solar system, like Earth and Mars are not tidally evolved, but in a compact system like TRAPPIST, everything just wants to become like circular and zero obliquity and very clean. But there's ways to depart from that a little bit, and that little bit can generate tidal heating.
Well, they're departed in eccentricity. They all have.
Yeah,
They have.
Yeah, a little bit.
Yeah. I was just wondering, isn't there some physics theory, like basically where tidal heating should be? You put it like either uniform or substellar or.
He's just playing around.
Yeah, I'm playing around, but I don't think so. I mean, I've talked to. Like I asked Rory this like 2 years ago, and he's like, "We don't have a theory for where the volcanoes are on Io." So I don't know this subject well enough, though. Like it may be that.
Does it depend that much dramatically on like what you have on the surface? Yeah, I would get think like tidal heating, either you get it in mantle or in the ocean. So basically something that
the different kinds of tidal heating. You can get tidal heating in the oceans and in the rheology of the world itself.
yeah, but I mean, unless you have
And this tidal heating they're talking about is mostly through the rheology. So it's through the solid rock that's getting heated by being squished like iron.
Okay, so but that should be more or less uniform, I guess, over the planet.
It should be more or less uniform.
So that means there should be some theory, I guess, which tells like where you actually.
Well, it's just heat dissipation inside, right? So it just depends on how the heat is transferred as it's being squeezed.
Well, it depends, I guess, of
what's
each part.
What's the conductivity of the rock? All these. Sort of
I don't think it needs to be uniform. And like I know volcanoes on Io are not distributed evenly, but I don't. I tried a literature review. I asked a couple people.
But I was thinking like in primitive forms, like for example, you have solid ball which is absolutely uniform, and you just deform it. Then presumably you should know like where your heating will be like.
Yeah. Well, you should do
there should be some analytical.
You should do some empirical experiments.
There should be some analytical formula, at least for some primitive case.
Perhaps. Okay, let's move on to Jan. Let's share the screen again. Come on. Share. Oh no, so you use this thing again. Let's do that. Okay, let's try. Hold on a second here. Let me find Jan's presentation. Okay. Okay, hopefully you all can see Jan's screen there. Okay, Jan.
Okay, so yeah, I've been working on the atmospheric dust cycle and dust cycle in Mars for a while, and it has been an ever-evolving project with different phases to which we have done here. I want to give a little bit an update on some stuff. So why do we want to have study dust ROCKE-3D for Mars? Mars is a very dusty planet, and we have dust storms occurring all the time. Every summer we have the dust storms that engulf the whole planet, and so it's a major factor for weather and climate variability, at least for present-day Mars. And so that is what we want to study. Here's a little table that shows differences between Mars and Earth. So I don't want to go through all of them. One is the very large eccentricity of Mars compared to Earth, which implies also large variations between the solar irradiance, between aphelion and perihelion, and that too very strongly determines the dust cycle of Mars. I'm not going to go into the details of the annual dust cycle. I want to focus on something else today. So for simulating Mars dust, we use the dust module that we have in the Earth system model, which simulates dust in 5 size bins for the dust cycle, for emission, transport, and deposition of dust, and in a total particle diameter range from between 0.1 and 32 micrometers. Dust emission is simulated using as a probability function with cube dependence on the wind speed, but formulated as a distribution where we also take into account a subgrid scale variability from various processes. We have preferential sources from topographic depressions, and soil, snow cover, and soil moisture are additional constraints in the model. We also have some explicit dependency on the atmospheric density. The emission factor is a free parameter in the model, so that is something we basically calibrate based on measurement data. So advection is one from it's the same as Model E, and for the tracer generally. For the removal we consider a dry position the new scheme that was implemented by Olivia, which is size dependent, and we also consider removal by collision with water ice particles, which is not a major process. We do not take into consideration any other interaction with the hydrological cycle or with for Mars may also be important with the carbon dioxide cycle.
So yeah, just to pick up on that first.
Yeah.
So do you think there in certain areas that the CO2 ice could play a bigger role than what you see for the water ice?
If we have frozen CO2 particles, it could be also maybe a form of condensation or something similar with like heterogeneous ice accumulation for water ice, which we don't take into consideration either in models. So that is something we should do, but in the future work.
But CO2 precipitation happens mostly during the polar night.
Yeah.
So basically, it's kind of away from the cycle mostly.
And paleo poles.
So for radiation, the model is coupled with the Socrates scheme, which for the relative transfer calculation, also for the relative effect of aerosols, and different to the Model E radiation scheme, Socrates also calculates scattering in the long wave range. So that was one of the things that we made a mistake in the past. And for the relative calculations, we consider 8 size bands for the smaller particle ranges. We use observations for one purpose is for calibration. We use for calibration of the dust cycle. We use the climatological, the dust optical depth data from Montabon, which is a synthesis of various instruments and has covered by now Mars year 24 to 36, but we only use 25 to 36 since year 24 uses some infilling from year 25, and so I didn't want to double count this. We use that for calibration. We use only the climatological global mean of the dust aerosol optical depth data, so we still can use these data for evaluating the spatial temporal distribution over the year. And for the vertical distribution, we use dust opacity from Mars climate sample retrievals. The experiments we run 20 years, 2 years where it's one way for spin up, and 18 years for the analysis. So we did experiments both for relatively active dust and relatively inactive dust for varying dust emission factors, and we tested various physics or test the sensitivity for various physics assumptions. Here I want to focus on the dust size distribution assumptions, since I think there's some interesting things to be shown. So that is one thing. My co-authors won't like to hear that, but I discovered earlier this week that I made a mistake in the input file for the horizontal distribution of dust emission. I'm confident enough to, since the mass size distribution will still be the same in the global average, I'm confident enough to show global averages and globally integrated data, but I don't want to show any horizontal distributions right now, since I don't want to implant any fast figures into your brains. And so that figure shows the simulated dust cycle for various variables and for these different size bins. These are two assumed size distributions. We don't really have any measurements for the emitted mass size distribution of dust. There are estimates for the size distribution of dust that are derived from opacity measurements, and then these measurements are different wavelengths, and then these measurements are fitted to assumed different or for various assumptions on the size distribution of dust, like assuming modified gamma distribution, and the best fit is then the estimate for the precise distribution. So we assume directly a certain mass size distribution of dust, which we took from Earth. So the blue one is what has been traditionally used in the model, in Model E, which is based on a power law distribution. And recently, in recent years, there have been works that the dust on Earth has actually larger particle sizes than previously thought, and the ROCKE size distribution is the one that we have in a publication a few years ago, where for the minimal version of the model, which is based on brittle fragmentation theory, and then augmented with a size distribution for large particles, which has been derived from measurements. So we just assume that we also can use these size distribution assumption for Mars. So we have much larger particle sizes for what I call AMF, aerosol minimum fraction method size distribution at emission, and that reflects then also in the global atmospheric dust mass. So the left bins, they show the size, the individual bins, and the right of the red line are the cumulative distribution. And the global dust dry deposition flux is very similar to the emission flux. The removal by collision is basically negligible compared to the dry deposition or simulations. So what I did. So for the calibration, we use the Montabone data, and the Montabone data are at 9.3 micrometers in the long wave range for the absorption optical depth. The model calculates the dust optical depth at 550 nanometers. As diagnostics, it calculates, of course, the whole spectrum, but the diagnostic only includes the 550 nanometers, so we use that these wavelengths for the calibration, and used conversion factor that Montabone gave from the absorption extinction at 9.3 micrometers to the visible extinction, total extinction at to the total extinction in the visible range, which is 2.6. So that in the upper right, for the cumulative extinction, the total dust matches that value for the optical depth, and then the size distribution depends on the described mass size distribution. We see that the larger contribution to the extinction at larger particles is seen in the AMF size distribution with a large particle emission. I calculated the dust aerosol optical depths then after the simulations, also for the other wavelengths, and since Montabone is a little bit unspecific, the conversion factor is set from the 9.3 micrometers to the visible or near infrared. Near infrared is very similar, so that is a relief. That is the post-calculated dust aerosol optical depths at 9.3 micrometers are simulated with a model. And if you look at the lower right panel, then there's actually a a large mismatch between the simulated dust aerosol optical depths and the value that is given by Montamon. So the 2.6, we get a different conversion factor for the aerosol optical depths. And for the absorption extinction and the visible extinction. So that our conversion factor would be for the blue size distribution about 6.5, and for the AMF size distribution about 5.5. So we don't really know what the size distribution is for dust on Mars. So, but what it shows is that the uncertainty is actually very large, and that that the assumption to just use that conversion factor is also not necessarily the right one. So I jump a little bit. We also compare to the MCS data. So Igor has shown before, so I'm jumping there. What I want to show that is, if we have these two different size distribution, that also has an effect on the relative effect of dust. This shows the direct dust relative effect from double calculation with dust, and then again for the same atmospheric state without dust. And what one can see is that the upper left shows the total scattering at the top of atmosphere. Let's focus on that. And that there is a significant difference between the two size distributions. The difference for the two calibrated simulations for the two size distribution is about 25% in scattering. So that is not little. And that, yes, I suppose that is only for the. Okay, so the takeaway here is that magnitude of the dust cycle is very uncertain. There's a strong sensitivity to the assumption on the middle dust size distribution. And what simulations like this maybe can do in the future is inform what is actually necessary to measure in Mars, in future Mars missions. That is one of the besides the scientific curiosity.
Thank you so much. Okay, we're going to move on. We have two more talks. Marshall's up next. Going to pause the recording.
Bottom and the ocean surface.
Okay, so Tony's up next.
You can talk after Tony's turn.
Okay.
Okay, so since it's already 5:30, I guess we're a bit ahead of time.
No, we're right on.
But this presentation won't take long anyway. Basically, I'm just going to show you the full treatment of the ocean dynamics at the poles, or basically getting rid of these damn land cells at the South Pole, which is a feature that's been requested for years now, especially by Mike. And so historically, when MODALI was developed, we had full ocean dynamics at the North Pole, but we didn't need any treatment of the ocean dynamic at the South Pole because we have the landmass there. Obviously, ROCKE-3D up until Planet 2.0 inherited this, and it's not an issue for Earth or any exoplanet that has a landmass at the South Pole. For example, Linda, I think the run that you showed earlier had a continent on the South Pole, so it wouldn't be an issue for this run. But all the other cases, whether it's an aquaplanet or an exoplanet with no landmass at the South Pole, that's an issue. So I guess we came up with a hackish way to circumvent that, where it was to put a land cell at the South Pole. But if you look in 3D, basically a land cell is like a giant wall at the poles. It's basically treating the ocean like a channel flow. And if you look at this schematic representation, if you have the land cell and you have an incoming wave in blue, it's going to be reflected against this giant wall. If you don't have any land cell there, it's just going to cross to the other side of the planet. So when we started the Europa project, maybe 3-4 years ago, we didn't have any treatment, obviously, at the South Pole for the ocean dynamics. When I started the setup for Europa, I put a land cell at both poles for symmetry reason. But I'm going to show you that it's only in an ocean. We only have an ocean configuration, but no, it's working. So this is the setup for our Planet 2 run with an ice shell of 15 kilometers sitting on top of a 60-kilometer deep ocean. We initialized the run with these values for the temperature and salinity. The gravity is a 1.4 meter per second square on Europa. We have in the first simulation, I'm showing you a constant geothermal heating at the bottom of the ocean, which is here, 10 watt per meter square. All the animations that you're going to see, it's 40,000 orbits around Jupiter. Europa orbit Jupiter in around 3.5 days. So 100 orbits is roughly equivalent to 1 Earth year. So 40,000 orbits is 400 years on Earth. And so I'm going to show you the first simulation with the land cells at the pole and the second simulation with the full treatment of the ocean dynamic at both the North and South Pole. So here we have the temperature and UVW, the three components of the ocean velocity. These are zonal average. So you have the depth here from 0 to 60 kilometer and the latitude here from 90 south to 90 north. So with the land cell, you can see you have a land cell at the pole with this little gray area on each side. That's what you get. I'm going to switch now to the run with the full ocean dynamics at the poles, and that's what you get. You see the heat rising at the top. The red line is what Kostas was showing. That's the tangent cylinder, and you can see a clear difference of regime between the region inside the tangent cylinder and the region outside of the tangent cylinder. And actually, yeah, this might be what we wanted from the beginning is to have exactly the same solution. Everything is symmetrical. The boundary condition, the forcings are symmetrical. So this might be the least impressive results for the most amount of work because basically you're going to see the exact same thing happening in the South Pole and the North Pole. The first row is the temperature. Bottom row is the magnitude of the velocity. The left is the North Pole, and the south is the South Pole. And well, these are quite hypnotic and trippy. But you see, basically, you have exactly it's identical to the beats on each side. I have a script that makes sure that everything happening in the North Pole, in the northern hemisphere, is the same, whether it's the temperature, salinity, or the velocity.
And this is even after 40,000 orbits.
Yeah, we're reaching. You have the count here.
Yeah, it's record 400.
Yeah. So now to get a bit more realistic, you might want to randomize the geothermal heating. So it's still around 10 watt per meter square. It was constant before, but it's randomized. Each cell is slightly randomized around 10 watt per meter square just to generate a more realistic ocean circulation. And obviously, we don't have symmetry anymore between both hemisphere, but that's what you get after 40,000. This is more realistic than a constant geothermal heating. This is for now with the treatment for the dynamics at the pole. And it might be easier to compare these side by side. The left column is the lens cells at the pole, and the right column is when you have the full treatments at the pole, and that this might be actually a good example why you might want a full treatment of the ocean dynamics, because it leads to a totally different ocean circulation. So you're going to see, for example, the bottom left, the magnitude of the velocity. You see all these currents bouncing against this giant wall, which is the cell at the southern pole. And after 40,000, you can see a totally different organization of the temperature and the currents on the right side. So I'm going to insist that that's what I'm saying on the last slide, that we might want to rerun some of the runs that we've done before, whether it's aquaplanets or exoplanets with where we had to put a lens cell at the South Pole, because that might lead to some quite different results in the end. The next step is know that the ocean part is working. We need to do the same thing to the sea ice dynamics. We don't have anyone left. James Williams was working on the sea ice dynamics, but he left two years ago, so I might have to do it myself, and then commit this to Climatic 2.03, which version it is.
If you can get it in.
So that everybody would be able to use now the full ocean dynamics. Yeah, well, I'm probably planning to write a paper on our Europa simulation, where now that we have there are a lot of other components going into the Europa simulation. The Europa runs were not the focus of this presentation. It was just to show you that now the ocean dynamics is working well.
So, Tony, did you fix sea ice dynamics also, or it's only?
No, that's what I'm saying. That's the next.
Okay, so they didn't touch yet.
So I will have to come with a different setup. I might use the core forcing. I can also, with the core forcing, you can do a run with no atmosphere, but the sea ice and the ocean. But once again, I will need to create a setup with a perfectly symmetrical condition. It's quite a bit time consuming to go into the code and fix everything.
Yeah, but I mean, for just regular runs, we still cannot use it. I mean,
right now, we would need to fix the CS dynamics before you can use that. Once we have both parts working, ocean dynamics and CS dynamics, then I can commit that to the Planet 2 repository.
The randomized geothermal heating, was this randomized in space only and then left constant, or the randomized in time?
Yeah, right now the example I showed was only randomized in space, but you could also write a function to randomize it in time.
Also, you don't have to randomize the geothermal heating. You could also introduce slight anomalies in the temperature field, initial temperature field, and you would converge to a similar solution. I've tried that. Works.
Butterfly effect. Anyway.
Okay. I think that's it. Thank you all for joining today. It was really great. As I said several times, there were so many great talks here and there wasn't enough time. So we have these bi-weekly meetings. Please sign up. Andrea sent the spreadsheet around again, the Google Sheet. So put your names there and share with us in more detail what you're doing, because all of you doing are incredibly interesting work, and it has implications for all of us. I think we have a lot to still contribute here. So please do that. I really want to see more of this work. So many beautiful simulations being done here. I'd love to see more of them.
And once in a while, until we get a building again, we can also meet here.
Yeah. To be arranged, 100%. That would be great.
Can you somehow push Gavin to get us IDs too?
You can ask.
I did, but it seemed like it.
Okay, we can discuss offline.
Yeah.
Okay, then we wrap it up. Turn it off. Thank you all.
And Mike,